Golden rivers of molten sugar swirl into shape as machines sculpt and polish the world's most iconic candies. Behind each bite of Starburst, Mentos, and Skittles lies a symphony of heat and flawless timing. Today we step inside the production lines to uncover the precise, mesmerizing process that transforms raw ingredients into colorful, chewy perfection. To craft Starburst, factories begin with a foundation of raw materials, with the primary ingredients being sugar, corn syrup, hydrogenated palm kernel oil, fruit juice concentrates, citric acid, and natural and artificial flavors. Food-grade colorants such as red 40, yellow 5, and blue 1 give the candy its vibrant, recognizable hues. Sugar, the dominant ingredient, is typically sourced from sugar beets or sugar cane, refined to a fine, white granulated form. Corn syrup, essential for achieving the chewy consistency, is extracted from dent corn and then enzymatically converted into glucose-heavy syrup. This syrup not only sweetens, but also inhibits crystallization, allowing for the distinctive, flexible Starburst chew. Fruit juice concentrates are selected based on seasonal availability and flavor profiles, often involving apple, cherry, orange, strawberry, lemon, and other citrus bases. Each concentrate is filtered and reduced under vacuum conditions to intensify the flavor while removing excess water. Meanwhile, citric acid, either derived from citrus fruits or biosynthesized using Aspergillus niger fermentation, is added to sharpen the tart notes and stabilize the pH level. Palm kernel oil, after undergoing hydrogenation to solidify its structure, contributes to the smooth mouthfeel, acting as a lubricant and textural agent within the candy matrix. All of these ingredients are delivered to the factory in bulk: sugar and corn syrup via silo systems and tanker trucks, oils in heated storage tanks, and flavoring agents in sealed food-grade containers to maintain freshness and prevent contamination. Once inside the facility, the first major step in the Starburst making process is ingredient weighing and batching. Massive computerized batching systems measure exact quantities of each component using load cells and automated valve controls. Sugar and corn syrup are combined in stainless steel jacketed mixing tanks where they are preheated to around 115 degrees Celsius. This begins the process of dissolving the sugar crystals into a homogeneous syrup base. Agitators inside the tanks ensure uniformity and prevent scorching. The heated syrup is then transferred to a vacuum cooker. In the vacuum cooking chamber, the syrup is exposed to reduced atmospheric pressure, allowing water to evaporate at a lower temperature. This technique is critical in candy making, as it prevents the sugar from caramelizing or breaking down under intense heat. As moisture is removed, the syrup thickens into a viscous mass with a specific Brix value, typically between 85 and 90% solids content, ensuring it will solidify into a chewy form once cooled. The exact cooking time and temperature are closely monitored via sensors and control systems linked to the plant's supervisory control and data acquisition platform, or SCADA. After cooking, the thickened candy mass is transferred through heated conduits into a mixing chamber known as a color and flavor cooker, or kneader. Here, hydrogenated palm kernel oil is added to help emulsify the mixture and control the final texture. Food-safe mixing blades, often paddle style or Z-blade types, churn the mass at controlled speeds. This is also the point where colorants, acids, and flavor concentrates are injected. High-precision peristaltic pumps ensure accurate dosing of color and flavor to maintain batch consistency, and the mixer is divided into multiple compartments if producing more than one flavor at a time. For instance, strawberry might be mixed in one chamber, lemon in another, and cherry in a third. Each batch customized with different concentrations of fruit essence and specific pH levels for optimal taste balance. Once the flavor-specific masses are ready, They must be cooled to a workable temperature, typically around 60 degrees Celsius, before shaping. Cooling belts equipped with air curtains and stainless steel rollers gently lower the temperature without causing hardening or premature setting. From here, the candy mass is directed into the forming line, a highly orchestrated system of extrusion, cutting, and wrapping. Extrusion is the next key phase. Using positive displacement gear pumps or auger-driven extruders, the warm candy mass is pushed through stainless steel nozzles with rectangular cross-sections. This creates long, continuous ropes of candy with a consistent width and height, matching the final Starburst dimensions. Servo motors carefully control the extrusion speed to synchronize with the downstream cutting process. If multiple colors or flavors are being co-extruded, special twin-screw extruders equipped with internal baffles can combine two masses into a single, dual-colored strand, which adds visual interest and flavor complexity. The ropes move onto a conveyor equipped with cooled rollers to maintain their shape. A high-speed guillotine cutter controlled by an optical sensor system slices the rope into individual blocks with precise timing. The cutting knives are made from food-grade stainless steel and are lubricated with a microfine spray of food-grade oil to prevent sticking. Each candy piece is now in its iconic rectangular shape, ready for wrapping. Wrapping Starburst is a marvel of mechanical ingenuity. Each piece must be individually wrapped in waxed paper to preserve freshness and prevent sticking. Automatic folding and wrapping machines, operating at speeds of up to 800 pieces per minute, perform this delicate operation with stunning precision. These machines use synchronized mechanical arms to position each candy, fold the wax paper around it using rotary folding drums, and seal it using gentle pressure rather than heat, which might soften the product. The wrapped pieces are then collated by vibratory feeders and assembled into 4-piece packs in various flavor assortments. These grouped candies are fed into a horizontal flow wrapper, where they are encased in the familiar branded packaging film. The flow wrapper uses a combination of rollers, film unwinders, photo eye sensors for alignment, and end-sealed jaws to create hermetically sealed packages that protect the candy from moisture and oxygen. The film is often reverse printed with branding, nutritional information, and batch tracking codes. Nitrogen flushing may be used in some production lines to displace oxygen and extend shelf life. After packaging, each unit passes through metal detectors and X-ray scanners to ensure there are no foreign objects or contaminants. Vision inspection systems verify print clarity, package seal integrity, and correct product count. Random samples are pooled for manual inspection by quality control technicians who assess texture, flavor, intensity, size, and appearance. Finished goods are then loaded into cartons by robotic case packers and labeled with lot codes for traceability. These cartons are palletized by robotic arms equipped with vacuum grippers, stacked in strategic configurations to optimize warehouse space and prevent crushing during transport. Once pallets are complete, they are shrink-wrapped and transferred via automated guided vehicles to temperature-controlled storage areas. Though Starburst is shelf-stable, storing it in a cool, dry environment prevents oil separation, flavor degradation, and textural hardening. From these warehouses, Starburst products are shipped out via freight trucks or distribution centers, eventually reaching retail shelves in supermarkets, vending machines, and convenience stores around the world. What makes the Starburst manufacturing process particularly interesting is the interplay between artistry and automation. While the ingredients themselves are simple, achieving the exact chewiness, vibrant color, and flavor burst that consumers expect requires precision-engineered machinery, tight process control, and an unyielding commitment to consistency. The smallest variation in moisture content, mixing speed, or cutting pressure could result in a piece that's too hard, too sticky, or aesthetically flawed. Despite being a candy rooted in simplicity, the industrial complexity behind Starburst underscores the broader evolution of confectionery manufacturing. Today's production lines incorporate real-time analytics, inline spectroscopy for flavor consistency, and even machine learning algorithms that predict equipment maintenance needs to avoid downtime. Some newer factories are experimenting with plant-based colorants and sustainable packaging materials, aiming to meet consumer demand without compromising on quality. There's even ongoing research into using recycled steam and closed-loop water systems to reduce the environmental footprint of candy production lines like those making Starburst. Mentos were first created in the early 20th century and gained global popularity due to their unique texture and intense flavor. The combination of a crunchy outer coating and a chewy interior is what sets them apart, and achieving that contrast requires precise formulation and processing. The base recipe revolves around sugar, glucose syrup, hydrogenated coconut or palm kernel oil, gelling agents like gelatin or modified starches, natural and artificial flavors, food-grade colorants, and glazing agents such as carnauba wax. Depending on the variety, mint, fruit, cola, or sour, the flavoring system will differ, but the core production mechanics remain largely the same. Production begins with the sourcing and handling of raw ingredients. Sugar is delivered in bulk form, typically refined cane or beet sugar, and stored in large silos within the factory. Glucose syrup, derived from enzymatically treated cornstarch, arrives in insulated tanker trucks and is stored in jacketed holding tanks to keep it fluid and at the proper viscosity. Oils are stored in temperature-controlled containers to maintain consistency. Each of these raw materials is subjected to a series of pre-checks. Sugar is tested for grain size and moisture content, glucose syrup for dextrose equivalent values, and oils for peroxide levels and stability. The factory's quality control department samples all incoming ingredients and verifies their compliance with specifications using chromatography, spectroscopy, and other chemical assays. Once approved, the first step in making Mentos centers on the formation of the candy core. Unlike many confectionery items, the chewy center of a Mentos is not extruded or cast, but formed using a process called compression or tableting. But before compression can occur, a slurry is created by blending sugar, glucose syrup, and oils in large mixing kettles equipped with paddle agitators. This mixture is partially cooked to evaporate water and develop the candy's elasticity. Once it reaches the desired consistency, typically with a Brix reading of about 85% solids, it is transferred to a cooling table where it is kneaded to achieve the ideal texture. The cooled mass is then broken into chunks and fed into a granulator, which reduces it into fine, uniform particles suitable for compression. These particles are sieved to ensure consistent particle size, which is critical for proper tablet formation. A binding agent, often modified starch or gelatin powder, is then added to help the particles fuse during compression. The powdered base is then fed into rotary tablet presses, high-speed machines equipped with stainless steel dies and punches that compress the powder into uniform cylinders. Each tablet is subjected to high compression force to achieve the dense, elastic core that is characteristic of Mentos. These presses can produce thousands of tablets per minute, and they feature real-time monitoring systems to ensure weight, hardness, and thickness are within specifications. The freshly compressed tablets are soft and not yet glossy. At this stage, they are known as centers and will undergo further processing to become the finished product. These centers are now ready for the panning stage, a method of coating used to apply multiple layers of sugar and flavor to build up the candy shell. The panning process takes place in large, rotating stainless steel drums called coating pans or Drageses pans. The cores are loaded into the pan, which rotates at a controlled speed while fine sprays of syrup, flavor, and color are applied in successive passes. Initially, a syrup consisting of dissolved sugar and glucose is sprayed onto the tablets using atomizing nozzles. Hot, dry air is simultaneously blown into the pan via air ducts, which rapidly evaporates moisture and causes the sugar to crystallize onto the surface of the tablets. This process is repeated over and over, sometimes more than 30 times per batch, to gradually build up the characteristic crunchy coating of Mentos. During these cycles, food-grade colorants and additional flavoring agents are also introduced. Different panning cycles are used for mint and fruit flavors. For example, mint Mentos typically receive a higher concentration of menthol and peppermint oil in the outer layers, while fruit Mentos require individualized flavor additions like strawberry, orange, and lemon, each blended with acidulants such as citric or malic acid to amplify the taste. Achieving uniform coating thickness, color distribution, and surface smoothness requires expert control of several variables: syrup viscosity, pan speed, airflow rate, and ambient humidity. Most modern Mentos facilities use programmable logic controllers and environmental monitoring systems to automate these parameters and ensure repeatability across batches. The entire panning process can take several hours, as each layer must dry before the next is applied. Operators use inline sensors and visual inspections to check for surface integrity, ensuring that no rough spots or cracks appear as the coating thickens. Once the desired shell thickness is achieved, the tablets undergo a drying and stabilization phase in climate-controlled holding rooms. Here, they rest for several hours, allowing residual moisture to equalize and the structure to firm up. The next step is polishing, a critical final touch that gives Mentos their trademark shine and smooth finish. Tablets are reloaded into specialized polishing pans and treated with a mixture of glazing agents such as carnauba wax and microcrystalline wax dissolved in ethanol or isopropyl alcohol. As the pan rotates, the wax mixture is sprayed lightly onto the surface of the tablets and then buffed by friction as the candies tumble against one another. This step not only enhances visual appeal, but also serves a functional role, creating a moisture-resistant barrier that extends shelf life. After polishing, the finished candies are cooled again to harden the glaze and prevent sticking. They are then conveyed to the packaging area via vibratory conveyors and sorting belts that align them into consistent orientations for loading. Modern Mentos factories use high-speed flow wrapping machines capable of packaging dozens of rolls per minute. The individual candies are fed into paper or plastic film wrappers, which are then heat sealed and crimped into the familiar cylindrical Mentos roll. These rolls are typically grouped into multi-packs or display trays using robotic case packers and then passed through labeling stations where batch codes and expiration dates are applied using inkjet or laser printing systems. To ensure food safety and quality, each roll passes through a series of automated inspection stations. X-ray machines and metal detectors scan for foreign objects, while vision systems inspect label placement, roll integrity, and seal quality. Statistical quality control sampling is performed by trained technicians who manually test rolls for chewiness, coating hardness, gloss level, and flavor profile using a standardized scoring system. Any deviations trigger a hold on the batch and a review of equipment calibration and ingredient records to pinpoint the source of variation. Pallets of Mentos rolls are finally shrink-wrapped and transferred to the factory's finished goods warehouse, where they are stored under tightly controlled temperature and humidity conditions. Though Mentos are relatively shelf-stable, proper storage conditions ensure they retain optimal flavor, texture, and appearance for months. From there, the products are distributed through regional logistics hubs to retail outlets around the globe. While consumers might simply pop a Mentos into their mouth without much thought, the reality is that each piece embodies a tremendous amount of behind-the-scenes engineering. From the uniform density of the core to the microscopic layering of sugar shell, every step in the process is fine-tuned to ensure consistency at massive production scales. Advanced data analytics platforms are increasingly being used in Mentos factories to track machine performance, ingredient variation, and environmental fluctuations, helping operators predict and prevent quality issues before they occur. The candy's production is also seeing innovations aimed at sustainability, including the use of biodegradable wrappers, energy-efficient panning systems, and closed-loop water recycling technologies. Some manufacturers are exploring plant-based gelling agents to create vegan-friendly versions of the product, expanding the Mentos appeal to a broader market while keeping the signature experience intact. The story of Skittles production begins with the sourcing of raw ingredients. The core of each Skittle consists primarily of sugar, corn syrup, and hydrogenated palm kernel oil, combined with fruit juice concentrate, citric acid, natural and artificial flavors, and gelatin or a plant-based gelling agent, depending on the variety. Food colorants such as Red 40, Yellow 5, Blue 1, and others provide the vivid, rainbow-like appearance, while carnauba wax is used for the final shine. All ingredients arrive at the factory in bulk, sugar in pneumatic tankers or super sacks, corn syrup in heated tank trucks, oils in insulated totes, and flavors and colors in sealed drums to preserve potency and prevent contamination. Once the raw materials are delivered to the facility, they undergo quality inspection. Sugar is tested for purity and grain size using optical sensors and moisture analyzers, while corn syrup is evaluated for its dextrose equivalent to ensure consistent sweetness and viscosity. The oils are checked for oxidative stability and melting point, and flavor compounds are tested with chromatography to confirm identity and strength. Approved ingredients are then routed to ingredient storage silos or intermediate tanks, each connected via stainless steel piping to the central mixing systems. The production of Skittles begins with the creation of the chewy center, which is not molded or extruded like many other candies, but rather formed through a process known as casting or deposition. First, sugar, corn syrup, and oils are combined in large, stainless steel, steam-jacketed kettles. Agitators mix the contents while the batch is heated to around 115 to 120 degrees Celsius. This heating step is critical. It dissolves the sugar, reduces viscosity, and activates the gelling agents that will give the Skittle its characteristic chewy texture. Once the mixture reaches the desired consistency, it is partially vacuum cooked to remove excess moisture, yielding a thick, elastic syrup. This candy mass is then deposited into starch molds, which are preformed trays filled with cornstarch that contains indentations for each candy. Depositing heads, essentially nozzles controlled by servo-driven pumps, release precisely metered amounts of the syrup into each cavity. These molds are then transferred via conveyor into a climate-controlled drying tunnel where they remain for 24 to 48 hours. During this time, water evaporates slowly and uniformly, and the chewy texture begins to set. After drying, the starch is separated from the candy cores using a destarching system. This equipment gently shakes and brushes off the remaining starch, which is collected, filtered, and reused in future cycles. The now formed Skittle centers are tumbled in large rotating drums to smooth their surface before being passed to the next critical step, the sugar shell coating, also known as panning. Panning is a cornerstone of Skittles production and one of the most technically demanding phases of the process. The centers are placed into enormous rotating pans, typically several meters in diameter, where the sugar coating is built up through dozens of thin layers. Each pan spins continuously, and while it does, a fine sugar solution is sprayed onto the candy centers. This syrup typically consists of refined sugar, glucose, water, and sometimes citric acid for tartness. Immediately after spraying, a blast of temperature and humidity-controlled air is directed into the pan, drying the surface and forming a thin, hard layer. This coating process is repeated many times, sometimes for several hours, depending on the desired shell thickness. Different flavor syrups are added at different stages if multiple fruit profiles are being used within the batch. The rotation speed, spray volume, airflow rate, and drying temperature are all managed by PLC-controlled systems that monitor pan performance in real time, ensuring consistency in shell formation. Operators oversee the process via touchscreen HMIs, adjusting parameters based on real-time data and sensory feedback from test samples. Once the shell has reached its final thickness, color is added. This is typically done with 1 or 2 additional layers of tinted sugar solution, each one custom formulated for a specific flavor variant. Red for strawberry, yellow for lemon, green for lime or apple, purple for grape, and orange for naturally orange. These solutions include FDA-approved food dyes, stabilized with acidulants and emulsifiers to ensure even distribution and adhesion to the candy surface. The result is a batch of candies, each uniformly colored, with a bright and durable outer shell. Next comes the finishing stage, where Skittles are given their unmistakable gloss. This is achieved using polishing pans and a mixture of carnauba wax and microcrystalline wax, sometimes diluted in alcohol to aid dispersion. The candies are tumbled gently while a fine mist of the wax solution is sprayed onto them. As the pan rotates, the candies polish each other through friction, creating a smooth, shiny finish. This step also provides a moisture barrier that helps extend shelf life and prevents the candies from sticking together in the package. After polishing, the Skittles are passed through cooling tunnels to solidify the coating and stabilize the structure. Then comes the critical stage of flavor sorting and portioning. High-speed sorting machines equipped with optical sensors separate the candies by color, using burst air jets to redirect them into designated channels. This ensures that each bag or pack of Skittles contains the full assortment of flavors in consistent proportions. The sorted Skittles are then conveyed to packaging stations, where they are portioned using volumetric or weight-based fillers. Each batch is dispensed into the appropriate packaging format, whether single-serve pouches, resealable share bags, or rigid tubes. The packaging film is reverse printed with branding, nutritional information, and traceability codes, and it is fed into horizontal or vertical form-fill seal machines. These machines form the pouches, fill them with product, and seal them in one continuous motion. Precise temperature and pressure controls ensure that the seals are airtight without melting the product inside. As the packaged Skittles exit the line, they are subjected to a series of inspection checkpoints. Metal detectors, X-ray systems, and vision scanners verify that each package contains the correct amount, is sealed properly, and is free of contamination. Random samples are pulled for quality testing, evaluating chewiness, shell thickness, flavor strength, and visual appearance. Some factories even use texture analyzers and sensory panels to verify that the candies meet brand specifications. Once approved, the packages are collated into cartons using robotic case packers and then palletized by automated stacking systems. Each pallet is stretch wrapped for stability and labeled with tracking information, including production time, line number, and batch code. Pallets are then routed to the warehouse, where they are stored in temperature and humidity-controlled conditions to maintain optimal product integrity. Skittles are remarkably shelf-stable, but proper storage conditions ensure that the texture remains soft and the colors do not fade. From the warehouse, Skittles are distributed via truck to retail distribution centers, grocery stores, vending machines, and online fulfillment facilities. The journey from raw ingredients to store shelves is timed to ensure freshness and consistency, with sophisticated supply chain software tracking every shipment to maintain inventory and respond to fluctuations in demand. The production of Skittles is not only an example of precision manufacturing, but also one of mass customization. Despite being produced in colossal quantities, every single piece must conform to strict standards of flavor, size, color, and texture. Innovations in data analytics, predictive maintenance, and machine learning are being introduced into Skittles factories to continuously improve yield, efficiency, and sustainability. Energy-efficient drying systems, water reclamation units, and biodegradable packaging research are helping the brand minimize its environmental impact without compromising the product's appeal. The history of Nerds stretches back to the early 1980s, when they were first introduced to the market as a playful, intensely flavored treat unlike anything else in the candy aisle. The appeal lay in their irregular shapes, their bright colors, and their signature combination of sweet and sour notes. Behind the scenes, however, the magic is created not by whimsy, but by a carefully controlled industrial process. It all begins with the sourcing of raw ingredients. The foundation of Nerds is refined cane or beet sugar, which arrives at the factory in bulk deliveries, often in multi-ton silos or in large paper sacks that are emptied into storage hoppers. This sugar is highly refined to ensure purity, with a moisture content so low that it will not clump during storage or handling. Alongside the sugar come shipments of corn syrup, which acts as a binding and texturing agent, as well as citric acid and malic acid to provide the tartness that defines Nerds' flavor profile. The plant also receives concentrated flavor oils and powdered colors approved for food use. Each batch of these ingredients is tested in a quality control laboratory before it enters the production stream, ensuring compliance with both flavor and safety standards. The production of Nerds begins with a core, which is essentially a tiny granule of sugar that serves as the seed for the candy's build-up process. These seed crystals are often derived from slightly coarser sugar grains that have been screened to a uniform size. The real artistry begins in the heart of the coating pans, large rotating drums that are the beating heart of sugar candy manufacturing. Inside these stainless steel pans, the sugar seed crystals are gently tumbled as a fine mist of sugar syrup is sprayed over them. This syrup is prepared in a heated mixing tank, where granulated sugar is dissolved into water under controlled temperature, often in the range of 110 to 130 degrees Celsius, and then blended with a precise amount of corn syrup to control crystallization. The hot syrup flows through jacketed piping to prevent premature cooling before being atomized into a fine spray within the coating pan. As the syrup coats the tumbling seed crystals, it begins to harden upon contact with the cooler air inside the pan, forming a thin outer layer. Then, a light dusting of dry sugar is sometimes added to further build the surface and maintain separation between individual granules. This cycle repeats dozens or even hundreds of times, each layer adding microns of thickness to the growing candy piece. Operators closely monitor airflow, humidity, and drum rotation speed to ensure that the candies do not stick together or form unwanted lumps. During this stage, the irregular shapes that make Nerds so distinctive begin to emerge. Unlike machine-molded candies that have identical geometry, these sugar-coating pans produce slight variations in size and contour, which means every Nerd has its own unique outline. The gradual layering process continues until the candy reaches the target size, which is typically just a few millimeters in diameter. Once the base size is achieved, flavoring and coloring are introduced. This is a delicate operation, as liquid flavors and colorants must be distributed evenly without dissolving the sugar surface. The pan operator reduces airflow slightly and sprays a concentrated solution of flavor oils, acids, and color onto the candy bed. In many cases, flavors are applied in small incremental sprays with pauses for tumbling in between, allowing the surface to dry and preventing color streaking. The flavors are carefully balanced so that the acids provide tang without overwhelming the sweetness, creating the signature taste that fans recognize instantly. After flavoring and coloring, the candies undergo a polishing step. This involves applying a thin layer of glazing agent, such as carnauba wax, which gives the nerds their characteristic sheen and helps protect them from moisture pickup during storage. The glaze is applied in a separate polishing pan, where candies are tumbled with a small amount of the molten wax until every piece has a uniform shine. At this point, the candies are allowed to cool and set fully, ensuring that their coatings have hardened completely. Cooling may occur in ambient air or in a temperature-controlled chamber that maintains low humidity to prevent stickiness. The fully cooled candies are then transferred via gentle vibratory conveyors to the packaging area. The packaging operation for nerds is an impressive example of precision weighing and high-speed filling. Because the candy pieces are so small and irregular, multi-head weighers are commonly used to ensure accurate portioning. These machines use multiple load cells arranged in a circular pattern, dropping small amounts of candy from each channel until the combined total matches the target weight. This system minimizes giveaway and ensures that each box contains exactly the promised amount. The iconic Nerds boxes are constructed from food-grade cardboard with an inner lining that protects against moisture. The packaging line begins by folding and gluing the flat-printed cartons into their box shape, often with automated carton erectors that can handle hundreds of units per minute. The weighers then deposit the precise quantity of candy into each box through stainless steel chutes. For dual flavor boxes, a partition is inserted inside the carton, and two separate weighing heads feed different candies into each side simultaneously. Once filled, the boxes pass through a closing station, where flaps are folded and glued shut, followed by a coding station that prints lot numbers and best before dates for traceability. The sealed boxes are then collated into larger trays or shrink-wrapped bundles for ease of handling in distribution. Quality control continues all the way through the process. In addition to the raw ingredient checks at the start, samples of candy are pulled from the line at regular intervals to assess flavor consistency, color uniformity, and physical integrity. The hardness of the coating is measured with specialized instruments, and the acidity levels are checked to ensure the sourness remains within the brand's signature profile. Metal detectors are integrated into the conveyor system to ensure no foreign materials make their way into the final product. From the packaging area, the candies move to the warehouse for distribution. Since Nerds are low in moisture and have a hard sugar shell, they are relatively stable during storage. However, they are kept in a cool, dry environment to maintain their texture and prevent color fading. Pallets of finished product are wrapped and staged for shipment to wholesalers, retailers, and export markets around the world. The journey from sugar seed to the vibrant, tangy pellets in your hand is a testament to how much engineering is hidden inside even the simplest candies. Each step, from syrup spraying in massive tumbling pans to the delicate flavor infusion and high-speed filling lines, is executed with precision to deliver the playful, crunchy experience that has kept Nerds popular for decades. Over time, manufacturing technology for Nerds has evolved to improve efficiency and consistency. Early production relied heavily on skilled operators adjusting pans by sight and sound. Today, advanced automation systems track humidity, airflow, and syrup application rates with sensors and feedback loops, ensuring that every batch meets exacting standards. The result is a product that remains faithful to its original flavor and texture while benefiting from modern advancements in food processing equipment. There is also increasing focus on sustainability in candy production. Many factories now recover and reuse heat from syrup cooking kettles, implement water-saving cleaning systems for coating pans, and work with suppliers to source sugar from more sustainable agricultural operations. Packaging too is being reevaluated, with lighter materials and improved recyclability being considered for the future. What makes the production of nerds especially fascinating is the balance between art and science. The process is rooted in classical confectionery techniques that date back centuries, yet it is executed on a scale and with a precision that only modern machinery can achieve. The slight variations in size and shape that give nerds their charm are not flaws, but deliberate results of the panning process, embraced as part of their identity. The story of Twizzlers begins long before the candy reaches the factory floor. As with many mass-produced confections, the foundation is in the sourcing of high-quality raw materials. The primary ingredient is refined wheat flour, which gives Twizzlers their chewy, slightly bread-like texture. This flour arrives at the plant in bulk tanker trucks and is stored in towering silos that protect it from moisture and contaminants. From here, it is gravity-fed or pneumatically conveyed through sealed pipes to the mixing area. Alongside flour, the recipe calls for corn syrup, which provides sweetness, binding power, and flexibility, as well as sugar, which boosts flavor and adds structure. Vegetable oil, often in the form of soybean or palm oil, contributes to the mouthfeel, while food-grade colors and flavorings give Twizzlers their signature appearance and taste. Every ingredient undergoes rigorous inspection in the quality control laboratory before it can be released to production. Flour samples are checked for protein content and moisture levels. Sugar is screened for crystal uniformity, and corn syrup is tested for viscosity and purity. Liquid flavors and colors are reviewed for consistency against reference standards. Once approved, ingredients move into the blending stage, where the transformation from raw material to candy dough begins. The mixing process takes place in large stainless steel horizontal mixers fitted with heavy-duty paddles or spiral blades. The operation starts with a precise ratio of flour and sugar being combined, followed by the gradual addition of corn syrup and water. These mixers operate under controlled speeds to ensure the dough develops evenly without excessive heat buildup. Oil is incorporated next, coating the flour particles and contributing to the dough's smooth, pliable consistency. Throughout mixing, operators monitor temperature and dough texture, making small adjustments to moisture content if necessary. In many plants, this step is partially automated, with sensors tracking torque resistance in the mixer to determine when the dough has reached the ideal elasticity. Once mixed, the candy dough is transferred to the extrusion line. This is the stage where Twizzlers take on their famous twisted rope form. The dough is fed into a large extruder, essentially a high-powered screw press that forces the material through a specially designed die. The screw inside the extruder rotates at a controlled speed, kneading and pushing the dough forward while maintaining an even temperature to prevent premature setting. At the end of the barrel, the die features multiple openings shaped to produce the exact cross-section of a Twizzler rope. For the classic variety, the die includes ridged channels that create the candy's spiral grooves. As the dough emerges from the die, it is still warm and soft, making it easy to shape but vulnerable to deformation. To preserve the precise geometry, the extruded ropes immediately enter a cooling conveyor, a long belt that passes through a tunnel where chilled, dehumidified air circulates. This step lowers the candy's temperature and sets the outer surface while maintaining a chewy interior. The speed of the conveyor is carefully calibrated so that cooling is uniform along the rope's entire length. An interesting detail of Twizzlers' production is that the twist in each rope is not solely a result of the die design. The conveyor belt itself may be equipped with rollers that gently rotate the ropes as they move forward, enhancing the spiral effect. The amount of twist is a delicate balance. Too much rotation can weaken the structure and cause breakage, while too little results in a less distinctive look. After cooling, the ropes are ready to be cut to size. Cutting is performed by high-speed guillotine blades or rotary knives synchronized with the conveyor movement to avoid crushing the candy. For standard snack-sized Twizzlers, lengths are typically between 6 and 8 inches, but the same line can be adjusted to produce miniature bites or extra long versions. The cut pieces now move towards the packaging area, but before they are boxed or bagged, they undergo inspection. Quality control technicians pull samples from the line to check twist uniformity, diameter, weight, and surface texture. The moisture content is measured to ensure the candy retains its chewiness during storage. Flavor is also evaluated by trained sensory panels who compare each batch to established taste profiles. Packaging Twizzlers is a study in efficiency. Depending on the product format, they may be wrapped in flexible plastic film, placed in cardboard trays, or sealed in resealable pouches. The packaging machinery begins with an in-feed system that gently aligns the ropes into uniform stacks. These stacks are then transferred into forming tubes where the plastic film is drawn around them, sealed along the edge with heat, and cut into individual packs. Heat-sealed jaws close the ends to lock in freshness and protect the candy from moisture and oxygen. Lot codes, manufacturing dates, and product identifiers are printed directly onto the packaging by inkjet or thermal printers, ensuring traceability for every unit. Sealed packages are collected onto a takeaway conveyor and then collated into larger cartons for shipping. These cartons are stacked on pallets by robotic palletizers, which arrange the boxes in stable patterns and wrap them in stretch film to secure the load. From here, the pallets are moved to the warehouse, a temperature-controlled environment designed to maintain product quality. Although Twizzlers are relatively stable due to their low moisture and high sugar content, excessive heat can cause surface stickiness or deformation, so storage temperatures are carefully regulated. The finished products are then shipped to distribution centers, retail outlets, and export markets. Behind all of this is a network of automation systems and process controls that keep production running smoothly. Modern Twizzlers plants rely on programmable logic controllers to coordinate mixer cycles, extrusion pressures, conveyor speeds, and packaging rates. These systems integrate with quality control data, enabling operators to adjust parameters in real time if a batch shows signs of deviation from the standard. The flavoring of Twizzlers deserves special mention. While the classic strawberry variety is the most famous, the process allows for a wide range of flavors, from cherry to chocolate to licorice. In each case, the flavor oils are blended into the dough at the mixing stage to ensure even distribution. The choice of flavor affects other parameters as well. For example, chocolate varieties may require a slightly different extrusion temperature due to the fat content in cocoa powder, while licorice varieties may use molasses or anise oil that alter dough handling characteristics. Over the years, Twizzlers production has been refined not only for efficiency, but also for consistency. Early methods required more manual handling, with operators guiding ropes off the extruder and cutting them by hand. Today's operations are highly automated, with minimal direct contact between workers and the product. This not only improves hygiene, but also allows for higher output with fewer defects. Sustainability is becoming a greater focus in candy manufacturing as well. Plants are investing in closed-loop water systems for cooling conveyors, energy-efficient ovens for any heat treatment steps, and waste reduction programs that recycle off-spec candy back into the mix when feasible. Packaging materials are also being evaluated for recyclability, with thinner films and plant-based plastics under consideration. What makes the Twizzlers process so fascinating is the combination of bakery-like dough handling with candy-making sweetness. The extrusion technology is similar to that used in pasta production, yet the ingredients and post-extrusion handling are firmly rooted in confectionery science. It is a hybrid process that demands both mechanical precision and an understanding of how sugars, starches, and fats interact under heat and pressure. When you pick up a pack of Twizzlers, you are holding the result of careful ingredient selection, finely tuned mixing and extrusion, precise cooling and twisting, and airtight packaging. Each rope is the product of countless micro adjustments in speed, temperature, and formulation that ensure the candy's texture, flavor, and appearance are exactly as consumers expect. The story of a Haribo gummy begins with the ingredients, each of which is selected for quality and consistency. At the heart of the recipe is gelatin, a protein derived from collagen that gives the candy its characteristic elastic texture. This gelatin arrives at the factory in dry, granulated form and must be carefully hydrated before use. Alongside gelatin, the formulation includes glucose syrup, often produced from wheat or cornstarch, which provides body, prevents crystallization, and contributes to the chewiness. Sugar is another mainstay, giving sweetness and structural integrity. Additional ingredients include citric acid for tartness, natural and artificial flavorings for each variety, and food-safe colorants to create the rainbow of hues that define Haribo's product line. Every batch of ingredients undergoes rigorous testing in a quality control laboratory before it reaches the main production floor. Gelatin is checked for bloom strength, which determines the firmness of the finished candy. Glucose syrup is tested for solids content and viscosity, ensuring it will flow and set properly in the cooking process. Flavor and color concentrates are measured for potency and compared against established standards. Only when the raw materials pass inspection are they released to the production team. The first major step in making Haribo gummies is the cooking process. This begins in large stainless steel vessels called dissolvers or cooking kettles. Here, sugar, glucose syrup, and water are combined and heated under controlled conditions. The heating process brings the mixture to a high temperature, often in the range of 110 to 140 degrees Celsius, allowing the sugars to dissolve completely and the syrup to thicken. Once the sugar syrup reaches the correct density, pre-soaked gelatin is added. The gelatin is never boiled, as high temperatures would damage its gelling properties. Instead, it is stirred in gently once the syrup has cooled to a safe range, typically between 80 and 90 degrees Celsius. At this point, flavorings, acids, and colors are added. For gummy bears, this might include lemon, orange, raspberry, apple, and strawberry flavor profiles, each paired with a corresponding color. The additives are metered in with precision pumps to ensure every batch is consistent in both taste and appearance. Stirring must be thorough but gentle to avoid incorporating excess air bubbles, which could mar the candy's surface. Once the mixture is fully blended, it is ready to be formed into shapes. This is where Haribo's distinctive starch molding process comes into play. The company uses a method called the Mogul system, an automated production line that allows liquid candy to be deposited into detailed molds with incredible precision. The process begins with large trays filled with a fine, dry cornstarch powder. This starch serves two purposes. It prevents the sticky candy from clinging to the trays, and it helps wick away excess moisture during the setting stage. Each tray passes through a stamping unit where metal dies press the shape of the candy into the starch. Tiny, bare outlines, cola bottle profiles, or whatever form is being produced. The impressions are crisp and exact, ready to receive the warm, liquid mixture. From the cooking kettles, the candy syrup is pumped through heated pipelines to a series of depositor nozzles. These nozzles align perfectly with the starch impressions and release measured amounts of syrup into each cavity. The depositor can switch flavors and colors quickly, allowing for multiple varieties to be produced on the same line with minimal downtime. Once deposited, the trays of liquid candy are conveyed into a long climate-controlled curing room. Here, they rest for 12 to 72 hours, depending on the recipe, temperature, and humidity. During this time, the gelatin network fully sets, giving the candy its final chewy texture, while the starch continues to absorb surface moisture. The curing rooms are kept at specific humidity levels to prevent the candies from drying out too much or becoming sticky. When curing is complete, the trays move to the demolding stage. The gummy shapes are gently lifted from the starch, which is recovered, dried, and sieved for reuse in future molding. Any excess starch clinging to the candies is removed through a combination of mechanical shaking and soft air jets. The gummies, now fully formed, have a matte appearance and a slightly tacky feel at this stage. To give them the glossy finish consumers recognize, the candies are transferred to large rotating drums called glazing pans. Inside, they are tumbled with a thin coating of food-grade waxes such as carnauba or beeswax, along with oils that enhance shine and prevent sticking. The glazing process is quick but crucial, as it also provides a protective barrier against moisture changes during storage. With their appearance perfected, the gummies proceed to the packaging area. Here, high-speed conveyors feed them into multi-head weighers, machines equipped with multiple hoppers that dispense exact amounts to achieve the target package weight. The candies are dropped into pre-formed bags or into the forming tubes of vertical form-fill-seal machines. These machines create a bag from a continuous roll of printed film. Seal the bottom, fill it with the candy, then seal the top in one continuous motion. For variety packs, sophisticated sorting systems group different gummy shapes and flavors in precise ratios before they reach the weighing step. This ensures that every bag contains the intended assortment. Packaging films are chosen for their barrier properties, keeping the gummies fresh while displaying bright branding. Each bag receives a lot code and best before date for traceability, then passes through metal detection equipment as a final safety measure. The finished bags are gathered into cartons, stacked onto pallets, and wrapped in stretch film to stabilize them for shipping. Pallets are moved to temperature-controlled storage areas until they are loaded onto trucks bound for distribution centers and retailers around the world. Throughout the entire process, quality control remains a constant presence. Samples from each batch are taken at multiple points, from syrup cooking to molding, curing, and packaging, to ensure that every aspect meets Haribo's specifications. Technicians test texture with penetrometers to confirm the perfect chew, measure pH to monitor acidity, and use colorimeters to verify hue accuracy. Flavor panels taste test samples to ensure the product matches established sensory profiles. The production of Haribo gummies has evolved significantly over the decades. Early batches were made by hand in small copper kettles and poured into starch molds one tray at a time. Today's lines can produce hundreds of thousands of pieces per hour, with computerized systems controlling every variable. Yet the core principles remain the same: quality ingredients, precise cooking, careful molding, and patient curing. There is also a growing emphasis on sustainability within Haribo's operations. Many plants now use energy recovery systems to capture heat from cooking processes, recycle starch indefinitely, and source gelatin and sugar from more sustainable supply chains. Efforts to reduce packaging weight and increase recyclability are also underway, ensuring that the joy of gummy bears has a smaller environmental footprint. What makes Haribo's process fascinating is the blend of old-world confectionery craftsmanship and high-tech automation. The mogul molding system, for instance, is an industry standard, yet it still relies on principles that candy makers have used for over a century. The long curing time is a reminder that some aspects of candy making simply cannot be rushed if the desired texture is to be achieved. By the time a bag of Haribo gummies reaches the shelf, it has undergone a transformation from raw sugar, syrup, and gelatin into a perfectly shaped, flavorful, and brightly colored treat. Behind each piece is a network of ingredient sourcing, controlled cooking, precision molding, and patient curing, all supported by layers of quality control and packaging expertise. Unlike traditional potato chips, which are sliced from whole potatoes and deep fried, Pringles begin life in the form of a dough. That's right, each Pringle is crafted from a carefully developed dough made from dehydrated potato flakes, corn flour, rice flour, and a precise mix of emulsifiers, oils, salt, and flavorings. This composition is no accident. It's designed for processability, uniformity, and that distinctive light, crispy crunch. The journey begins with sourcing and preparing the raw ingredients. Dehydrated potato flakes, the primary ingredient, are supplied by potato processing plants that convert whole potatoes into a dry, shelf-stable form. These flakes are produced by washing, peeling, cooking, mashing, and finally drying the potatoes into flakes through a drum drying or belt drying process. The quality of these flakes is critical. They must have consistent moisture, starch, and texture characteristics to behave predictably in the Pringles dough. In the factory's raw materials storage area, huge silos hold the potato flakes, as well as corn flour and rice flour. These are conveyed through enclosed pneumatic systems into high-capacity ingredient blending hoppers, where each component is dosed with incredible accuracy. Every batch of dough requires precision, down to the gram, to ensure the final product maintains the correct structural properties, color, and flavor balance. Ingredients are mixed in a horizontal ribbon blender or paddle mixer, often in batches of several hundred kilograms at a time. Water is then added gradually to the dry mix, and the entire mass is blended under tightly controlled conditions to form a malleable, uniform dough. The water temperature, mixing time, and total moisture level are all carefully monitored by PLC-controlled systems. The dough must be neither too dry, resulting in cracking during forming, nor too wet, which would lead to expansion or puffing during frying. Instead, the goal is a smooth, pliable dough with a clay-like consistency that can be shaped, cut, and fried without distortion. Once the dough is ready, it's transferred via conveyor to the sheeting line. This is where the process becomes highly visual and mechanical. The dough enters a series of rotating rollers, which press it into a continuous thin sheet, about 1 to 2 millimeters thick. These rollers apply uniform pressure across the width of the belt, creating a dough sheet that is even in thickness from edge to edge. Sensors above the belt continuously scan the sheet for thickness deviations, triggering automatic adjustments if needed. Next, the dough sheet passes under a rotary cutter, a drum outfitted with precision-engineered dies in the shape of the iconic Pringle oval. As the cutter rolls over the moving dough sheet, it cuts out uniform ovals, which are gently lifted off the belt using a vacuum system or pickup fingers and placed onto metal cooking molds. These molds are slightly concave to give the chip its characteristic hyperbolic paraboloid shape, often referred to as a saddle curve. Any leftover dough between the cutouts is collected by scrapers, rehydrated, and recycled back into the mixing process. This near zero waste approach is one of the key efficiencies of the Pringles process. It's also one reason the chips are so uniform. Every piece of dough goes through the same treatment again and again until it reaches the fryer. Once placed on the curved molds, the uncooked Pringles move via conveyor into the continuous fryer. This piece of equipment is massive, often stretching 10 to 15 meters in length, and filled with high-stability cooking oil, usually sunflower or corn oil, heated to around 180 degrees to 190 degrees. As the metal trays holding the chips travel through the fryer, the dough crisps into its final form. Each chip is fried for a precise duration, usually between 10 and 20 seconds, to ensure it emerges golden, crispy, and with the exact moisture content required for long shelf life and a satisfying snap. Because the chips are held in molds during frying, they maintain their consistent curve and do not puff or fold. This gives them the clean, stackable quality that defines the brand. The oil used in the fryer is continuously filtered and topped up to maintain purity and minimize off flavors. Inline sensors monitor the oil temperature, flow rate, and chip throughput to keep the process optimized at all times. After frying, the chips pass through an oil drain section, often assisted by compressed air jets or vibrating conveyors that shake off excess oil. The chips are then conveyed to a cooling system, a multi-stage area where fans and ambient air bring the chip temperature down quickly but gently. Proper cooling is essential before flavor application. Too much heat and the flavor powders will degrade or fail to adhere properly. Once cooled, the Pringles are directed into the seasoning tumbler. This is a large, rotating stainless steel drum where chips are gently tumbled while dry flavoring powders are sprayed or sifted onto their surfaces. A light mist of oil may be reapplied before this step to help the powders stick. Seasoning can include classic salted flavors, sour cream and onion, barbecue, cheddar, or custom blends formulated in-house by flavor scientists. Each seasoning blend is composed of salt, acids, cheese powders, natural and artificial flavors, and sometimes even encapsulated aromas that release in the mouth. As the chips roll through the seasoning drum, every surface is coated evenly thanks to the drum's speed, angle, and baffle design, which keeps the product moving in a gentle, randomized pattern. The process is engineered so that not only is flavor distribution even, but breakage is kept to an absolute minimum. After all, uniformity is part of what makes a Pringle a Pringle. Once flavored, the chips proceed to the stacking station, a marvel of mechanical choreography. Conveyor belts equipped with sensors and robotic arms gently align the Pringles into neat vertical stacks, each containing an exact number of chips per tube. As the stacks are formed, they are transferred onto a platform that slides them into waiting Pringles cans, the brand's signature packaging that also serves as a structural support, keeping the delicate chips safe from breakage. As the neatly formed stacks of Pringles are guided toward the packaging area, we enter one of the most unique elements of the brand's manufacturing process: the creation and loading of the Pringles canister. Unlike traditional snack foods that use pillow bags or plastic trays, Pringles uses a rigid composite can designed to protect the delicate stacked chips from breakage and to maintain freshness for extended periods. The Pringles canister is a marvel of engineered packaging. It's made of composite cardboard wound into a cylinder with a metal foil-lined bottom and a plastic snap-on lid. Each element of the can is optimized for shelf life, stacking strength and brand identity. The inner lining of the can is coated with a thin layer of aluminum foil or a moisture-resistant laminate that acts as a barrier against humidity and oxygen, two of the biggest enemies of fried snack foods. The exterior, of course, is wrapped in a colorful printed label indicating the flavor, nutritional information, and branding. In the packaging area of the factory, canisters are assembled and formed on-site or delivered pre-formed, depending on production volume and facility layout. High-speed rotary machines apply the foil bottoms to each cardboard tube using a heat or adhesive sealing process. Once the bases are sealed, the empty cans are conveyed toward the chip stacking zone, where robotic systems are already preparing the next batch of perfectly formed chip stacks. With the chips cooled, seasoned, and stacked into uniform columns, a synchronized pusher arm aligns with the moving conveyor and gently nudges each stack into the open can. This is done with remarkable precision. Too much force and the chips will crack or compress. Too little and the stack may tip or shift inside the can. Every stack is composed of a standard number of chips, most often between 80 and 100, depending on flavor, region, and package size. Weight sensors downstream confirm each can's fill weight to verify proper loading. Next, each filled can passes through a nitrogen flushing station. This is a vital step in the preservation process. Before the plastic lid is applied, a short blast of food-grade nitrogen gas is injected into the can to displace any oxygen. Nitrogen is inert and doesn't react with fats or seasonings, making it ideal for extending the shelf life of fried foods. By eliminating oxygen, this step slows down oxidative rancidity, preserving the taste, aroma, and crunch of the chips for several months. Immediately after flushing, the snap-on plastic lid is applied. These lids are manufactured from injection-molded polypropylene or polyethylene and are flexible enough to form a tight seal without adhesives. In some cases, a foil pull tab seal is applied just below the lid for additional freshness protection or tamper evidence, especially for export markets or special edition products. Once sealed, The cans are rotated and conveyed through label verification systems, where barcode scanners and cameras inspect each label for alignment, print clarity, and proper coding. Date codes, production line identifiers, and batch numbers are printed on the can's bottom using high-speed inkjet or laser printers. These codes are crucial for traceability in the event of a recall, complaint, or audit. From here, the sealed Pringles cans are grouped into secondary packaging formats. Depending on the market and distribution requirements, this could include shrink-wrapped multi-packs, shelf-ready trays, or corrugated cartons. Robotic arms equipped with suction cups or pneumatic grippers stack cans horizontally or vertically into their assigned configurations. These groups are then passed through a heat tunnel to shrink-wrap them into a durable bundle, or they are placed directly into cartons for larger shipments. At this point, each grouping is staged for palletization. Robotic palletizers pick up completed cases and organize them into layered patterns optimized for space and stability. Each layer of cases is carefully aligned to minimize shifting during transportation. Once the pallet is fully loaded, it is automatically wrapped in stretch film and labeled with a unique shipping ID. This barcode ties the pallet to a digital inventory management system that knows its contents, weight, destination, and production timestamp. Before any pallet leaves the factory floor, strict quality control protocols are enforced. At multiple stages along the line, from dough mixing to packaging, line workers and QA technicians pull random samples for analysis. These samples are tested for moisture content using gravimetric or infrared drying methods, oil content using Soxhlet extraction or near-infrared analysis, color using colorimeters calibrated to Pringles' specific golden hue, breakage percentage by simulating drop and vibration tests, flavor uniformity through sensory panel evaluations conducted in specialized tasting booths. Each facility maintains a detailed product specification profile for every flavor. If any attribute, texture, taste, size, weight, falls outside these boundaries, corrective actions are triggered. This might include rebalancing the dough mix, adjusting fryer dwell time, recalibrating seasoning dispensers, or reprogramming stacking arms. In rare cases, product may be quarantined and destroyed if it fails microbiological or allergen controls. In parallel with physical testing, real-time data monitoring systems are constantly logging hundreds of variables across the plant. These include fryer oil, turnover rate, seasoning application rates, cooling tunnel temperatures, nitrogen pressure, and wrapping line speed. Plant operators access these through human-machine interface terminals, which are integrated with supervisory control and data acquisition systems. These tools allow live oversight of every critical process and make troubleshooting faster, smarter, and more proactive. Food safety is paramount throughout the entire operation. The plant is designed around zoning principles to minimize cross-contamination, meaning that raw ingredients, in-process dough, cooked product, and finished goods all move through different hygienic areas. Airflow systems, sanitation teams, and stainless steel equipment ensure compliance with GFSI, FDA, and ISO 20000 standards. Allergen controls, cleaning schedules, and traceability systems are regularly audited by third-party certification bodies. Meanwhile, sanitation and efficiency go hand in hand. After each production run or flavor change, the line undergoes a full clean-in-place procedure. Dough mixing vessels are flushed, sheeters and cutters are wiped down, seasoning drums are vacuumed, and oil is filtered or replaced. All maintenance events are logged digitally, and any anomalies in cleaning schedules are flagged for review. In terms of sustainability, the Pringles production system has also evolved. Cooking oil is now often recycled and re-refined after filtering. Off-spec product, chips that are broken, underfried, or misflavored, are collected and ground into animal feed or converted to energy through anaerobic digestion. Waste heat from fryers is repurposed to preheat incoming processed water. Even packaging waste from trimming labels or misprinted cartons is collected, baled, and sent to specialized recyclers. But sustainability doesn't stop at waste. Modern Pringles facilities are optimizing energy efficiency through LED lighting, variable frequency drives on motors, and smart climate control systems that adjust airflow based on production load. Water used for cleaning is recovered in greywater systems. Solar panels are increasingly being added to roofs to offset peak energy usage during day shifts. Through this carefully choreographed sequence of machines, materials, software, and sanitation, millions of Pringles cans are produced each day, all identical in shape, taste, texture, and crunch. From a seemingly simple snack emerges one of the most standardized and technically refined food production systems in the industry. A Pringle isn't just engineered for flavor, it's engineered for repeatability. As Pringles production ramps across continents, the factory processes remain largely uniform, but the flavors do not. While the foundational chip recipe is remarkably consistent from one country to the next, flavor development is where regional preferences and culinary creativity come alive. From seaweed in Japan, to paprika in Germany, to chicken tikka masala in the UK, the Pringles lineup is a testament to how food science adapts to global taste trends without compromising product structure. The development of new flavors starts at specialized flavor research and development centers, often housed within or adjacent to major production facilities. These flavor labs are equipped with pilot-scale processing lines that mirror the main production environment, but in miniature. Here, food scientists and flavor chemists experiment with combinations of spices, acids, aromatic oils, and flavor precursors, blending them into fine powders that can be dry applied or oil dispersed for coating. The process begins with a flavor brief, a document informed by market research, consumer data, and regional food trends. For example, in Southeast Asia, there's a growing demand for heat, umami, and fermented flavors, whereas North American markets favor bold, smoky, and cheese-forward profiles. Once the flavor direction is defined, formulation begins. This involves building the flavor in layers: top notes, middle notes, and base notes. These powders are then micro-tested in pilot seasoning drums using small batches of real Pringles. A cross-functional team of experts, including sensory scientists, marketing professionals, and regional representatives, sample the chips in structured sessions. Evaluations are made not only on flavor intensity and balance, but also on how the seasoning adheres, how it evolves during chewing, and whether it leaves any residual texture or off notes. To quantify this, descriptive sensory analysis is used. Trained panelists score each chip along standardized scales. For example, sourness, saltiness, umami, flavor longevity, and clean finish. These scores are matched against existing products and flavor targets to determine whether the new blend is viable. Adjustments are made repeatedly. A flavor might need more lactic acid for tang, less maltodextrin for stickiness, or more encapsulated compounds to preserve aroma during frying. Once a flavor passes these internal benchmarks, it's subjected to consumer testing. Often conducted in controlled booths or simulated living rooms, participants sample the chips blindly and provide feedback on liking, uniqueness, and purchase intent. Only the highest scoring candidates proceed to production scale rollout, and even then, factory adaptations are needed. New flavors may require adjustments in drum angle, rotation speed, or seasoning flow rate to achieve even coverage without waste or dust buildup. Interestingly, not all flavors can be produced on the same lines without risk. Facilities follow strict allergen management procedures. For example, cheese-based flavors often contain milk derivatives and must be run on separate lines or in dedicated shifts with full clean-out protocols between runs. Flavor dust may linger in filters or ducts, so cross-contamination risks are carefully managed through scheduling, deep cleaning, and validation swabbing. Once production begins, logistics take over. Distribution is a global operation. From factories in the US, Europe, and Asia, Pringles are shipped to more than 140 countries. The logistics chain is engineered to minimize time between production and shelf while protecting product integrity. Pallets are stored temporarily in automated storage and retrieval systems, massive, high-density warehouses controlled by software that manages FIFO protocols and precise temperature conditions. From there, transport trucks are loaded for regional delivery. In most climates, Pringles can be shipped in ambient dry vans as long as the temperature remains below 30 degrees Cs. However, in hotter regions or during summer months, climate-controlled containers are used to prevent oil migration, flavor deterioration, or packaging distortion caused by heat. As a product reaches retailers, the packaging does more than just protect, it sells. The Pringles canister has undergone subtle yet meaningful changes over the years. Originally designed for durability and storage, it has been adapted for visibility and ergonomics. Modern designs feature bold color blocking, QR codes for promotions, and tamper-evident seals in some countries. In-store, Pringles are often displayed vertically to highlight their stackability, or horizontally to emphasize flavor variety. Multi-pack bundling strategies vary by region. In North America, shrink-wrapped tri-packs are common. In Europe, tray displays dominate, and in Asia, mini-can multi-flavor assortments are especially popular among younger demographics. Parallel to the consumer-facing systems, there's a silent but powerful force ensuring Pringles quality. Shelf life stability testing. In dedicated labs, accelerated aging chambers expose Pringles samples to high humidity, elevated temperatures, and UV light. These conditions simulate long-term storage to test how the chip's texture, flavor, and aroma evolve over time. Chemical analyses measure oxidation markers in the oil. Sensory panels check for flavor loss, stale notes, or rancidity. Packaging engineers also test barrier properties of the canister, evaluating oxygen transmission rates, moisture vapor transmission rates, and mechanical integrity. The rigid tube structure gives Pringles an advantage over bagged snacks in this area, but continuous improvement efforts focus on reducing material usage while maintaining performance. Sustainability teams investigate new liner films and lid materials to improve recyclability without compromising shelf life. Meanwhile, every Pringles manufacturing facility operates with a documented traceability system. If a single issue is reported, say a foreign object or off flavor, teams can trace the affected batch back to its raw material inputs, processing line, timestamp, and even the maintenance records of involved equipment. This level of accountability is not just for crisis management, it's also a pillar of continuous improvement under Lean or Six Sigma methodologies. Plant managers review key performance indicators daily, tracking metrics like yield efficiency, chip breakage rate, seasoning variance, and energy usage per ton of product. Teams hold daily Gemba walks, on-the-floor audits, where operators and supervisors jointly inspect equipment, cleanliness, and line balance. This close attention to detail helps ensure that every Pringle, from the first to the last in the tube, is as perfect as the brand promises. This dedication to operational excellence supports global expansion. In newer markets, Pringles are often co-manufactured with partners who undergo extensive onboarding and validation audits to match the parent company's process control standards. These partners receive the exact mold geometry, dough specifications, seasoning formulas, and quality test protocols to replicate the product faithfully, no matter where in the world it's produced. As the product circulates through global supply chains, consumer feedback plays an increasingly important role. Online reviews, customer service inquiries, and social media sentiment are continuously analyzed by AI tools that flag trends, positive and negative. If flavor fatigue emerges or a packaging flaw becomes evident, insights are routed back to R&D and production teams. In some cases, limited-time flavors are revived based on nostalgia or regional demand spikes, giving rise to special editions like Buffalo Ranch, Pizza Supreme, or Hot and Spicy Jalapeno. This agile, responsive production model allows Pringles not only to maintain its core consistency, but also to evolve. The ability to innovate at scale without compromising the chip's fundamental identity is a core part of its success. If there's one feature that sets Pringles apart from every other chip on the market, it's their shape, the hyperbolic paraboloid. This unique, saddle-like curve isn't just for aesthetics, it's a product of meticulous structural engineering, specifically designed to deliver maximum stacking efficiency, uniform frying, and a signature mouthfeel unlike any flat or crinkle-cut chip. The curvature allows each chip to nest perfectly into the next, eliminating air pockets and wasted space in the canister. This design minimizes breakage during shipping and provides the visual appeal of a clean, organized stack. But it goes deeper than logistics. The curve also impacts how the chip fractures during the bite. Unlike irregular chips that snap inconsistently, Pringles break with a clean, predictable crunch. This fracturing behavior is something food texture scientists study intensely, using acoustic and mechanical analysis. In fact, the crunch curve of a Pringle is measured by placing a chip under a pressure gauge fitted with sound sensors. The chip is compressed until it breaks, and both the pressure profile and the acoustic signature are recorded. A good Pringle has a quick, brittle break with minimal flex, translating into that unmistakable first bite sensation. If the chip bends too much before breaking, it feels stale. If it's too brittle, it shatters into crumbs instead of neat fragments. This attention to mechanical bite quality is supported by consistent thickness, oil content, and starch structure, all regulated at every stage of production. Even the dough's amylose to amylopectin ratio is fine-tuned during potato flake selection and mixing, influencing how the chip cooks, colors, and crisps. But beyond shape and sound, there's also the Pringles mouth melt. As the chip dissolves, the oil, salt, and flavor particles spread evenly across the tongue, engineered to deliver a balanced flavor wave. First salty, then tangy, then savory or spicy, depending on the variant. This progression is no accident. It's the result of controlled particle sizing in seasoning powders, fat coating mechanisms, and even saliva-soluble flavor compounds embedded in the chip matrix. The result is a snack that engages multiple sensory systems at once: crisp auditory feedback, light mechanical resistance, aromatic release, and lingering taste. This multisensory synchrony is a big part of why consumers find Pringles both addictive and oddly satisfying. It's also what makes them so instantly recognizable. Without even seeing the logo, people know they're eating a Pringle the moment they hear that first crunch. A crisp snap, a creamy melt, and a perfect balance of chocolate and wafer. KitKat is more than a candy bar. It's a confectionery icon, loved worldwide and instantly recognizable for its 4 slender fingers and clever tagline. KitKat stands as a shining example of how precision engineering, food chemistry, and high-speed automation can come together to craft something remarkably simple and yet technically intricate. To understand how KitKat is made in a factory, we have to start with its dual nature: half chocolate, half wafer. Each must be manufactured independently with extreme care, then combined at the right moment to create a product that tastes the same, whether it's made in Japan, the UK, or Canada. The process begins with the preparation of raw ingredients, and the base of it all is wheat flour, used for the crispy wafers. This flour is stored in towering silos, aerated and filtered to remove dust and contaminants. It's pneumatically conveyed to the mixing room, where it's combined with sugar, palm or sunflower oil, milk powder, salt, baking powder, and water. These ingredients are deposited into large, jacketed horizontal mixers, which knead them into a consistent, homogeneous dough. At this stage, automation systems monitor dough temperature and hydration levels, adjusting mixer speed and timing accordingly. Once the dough is ready, it's extruded into thin sheets. This happens on massive wafer sheet lines, flat conveyor belts, where rollers press the dough into sheets less than 2 millimeters thick. These sheets move through high-capacity baking ovens that use convection heat to evenly cook them. These ovens stretch over 50 feet long, operating at temperatures around 180-200 degrees. Each wafer sheet bakes for less than 2 minutes, but emerges dry, crisp, and golden, ready for layering. Now comes one of the most signature features of the KitKat, the layered wafer structure. Each wafer sheet is passed through a slathering station, where a precise amount of wafer cream, a chocolatey, fat-based paste, is applied to its surface. This cream, made from finely ground sugar, fats, milk solids, and cocoa powder, serves as both flavor and adhesive. Multiple layers of wafers and cream are stacked, typically 3 wafers and 2 cream layers, forming a block known internally as a wafer book. These wafer books are pressed under light pressure and sent through cooling tunnels to stabilize the cream. Once firm, they are sliced into individual fingers using ultra-sharp guillotine blades or water jet cutters. Each finger is a perfect rectangle, dimensionally identical to ensure they fit precisely into the chocolate molds in the next stage. Meanwhile, chocolate production is running in parallel. KitKat uses milk chocolate, which must be refined and tempered to perfection. The chocolate begins with cocoa liquor, cocoa butter, milk powder, and sugar, all blended together in mixing tanks. From there, the mixture is passed through refiners, a series of large rollers that crush and flatten the mixture into particles smaller than 20 microns. This size is critical to achieving the smooth mouthfeel expected of high-quality chocolate. After refining, the mix enters conching machines, giant heated vats where the chocolate is stirred, aerated, and aged for several hours. This removes bitter volatiles, improves texture, and develops flavor. Once conching is complete, the chocolate is tempered, a precise process of heating, cooling, and reheating the chocolate to promote the formation of stable cocoa butter crystals. Without this step, the chocolate would be dull, soft, or prone to blooming. Tempered chocolate has a shiny finish, satisfying snap, and melt-in-your-mouth consistency. Now the chocolate and wafer fingers are ready to unite. This happens on a molding line. First, plastic or stainless steel molds are warmed slightly and filled with a thin layer of tempered chocolate. This bottom layer forms the base of the KitKat. Then, the pre-cut wafer fingers are robotically placed onto the chocolate-filled molds. Another dose of chocolate is deposited over the top, fully enrobing the wafer fingers and completing the bar structure. The filled molds pass through a vibration table to remove air bubbles and ensure complete coverage. From there, they travel through a cooling tunnel, a refrigerated chamber where the chocolate crystallizes and solidifies. By the time the molds exit, the KitKat bars are fully formed, firm, and ready to be demolded. Demolding is fully automated. Each mold is flipped, and a gentle mechanical tap releases the bars onto conveyor belts. The now empty molds are cleaned, sterilized, and recirculated back into the system. The KitKat bars now move to quality inspection. Vision systems equipped with high-speed cameras scan every bar for size accuracy, surface defects, cracks, or incomplete coatings. If anything is off-spec, that bar is removed from the line. Approved bars continue on toward the flow wrapping station. Packaging is a crucial part of the KitKat experience, not just for branding, but also for shelf life. Each bar is wrapped in metallized plastic film that acts as a barrier to light, oxygen, and moisture. The flow wrappers operate continuously. Bars are fed onto belts, aligned by guide rails, and pushed through a forming collar where the film is wrapped around them and sealed with heat-sealing jaws. Wrapped bars are then grouped into multi-packs or secondary trays, depending on customer requirements. Robotic arms or pick-and-place machines assemble the bars into display-ready formats. These units are then placed onto pallets using automated palletizers and stretch-wrapped for transport. Every step of this process is monitored by SCADA systems and connected sensors. Mixing temperatures, dough moisture, oven humidity, chocolate viscosity, flow speeds, and packaging integrity are all logged in real time. If a parameter drifts outside the set range, alerts are triggered and corrective action is taken immediately, either by automatic control or operator intervention. Meanwhile, samples from every production lot are pulled and sent to the on-site quality assurance lab. Here, technicians run texture analysis, moisture content testing, shelf stability trials, and most importantly, sensory evaluations. Trained tasters assess whether the product matches the official profile: crisp but not dry, sweet but not cloying, and a melt that delivers the cocoa hit right before the wafer crunch. Beyond quality, KitKat factories are also designed with hygiene and allergen safety in mind. Separate lines may be maintained for peanut-free or gluten-free variations, and full allergen switchover protocols are implemented if recipes change. Stainless steel surfaces, clean-in-place systems, air filtration, and pressure-zoned rooms ensure that each environment is sanitary and safe. Sustainability is also an emerging pillar of KitKat's production. Many factories now source Rainforest Alliance certified cocoa, and water and energy recovery systems are implemented to reduce waste. Chocolate scraps and wafer trim are collected and reprocessed, either reused in internal production or recycled into other food streams. From raw wheat and cocoa beans to precision molded chocolate fingers, the production of KitKat is a dance of science and craftsmanship. It's easy to take for granted, something you grab at the store, tear open, and snap into without a second thought. But behind every bar is an extraordinary feat of coordination, timing, and innovation. It's the result of countless variables, all controlled within narrow limits, to ensure that when you have a break, you're rewarded with the exact flavor, texture, and snap you expect. Golden foil, delicate layers, creamy filling, and a whole hazelnut at the core. Ferrero Rocher is the epitome of premium chocolate craftsmanship. But what seems like a luxurious, handcrafted treat is actually the result of one of the most precise and sophisticated chocolate manufacturing operations in the world. Produced by the Italian confectionery giant Ferrero Group, Ferrero Rocher is a marvel of layered architecture and synchronized automation. And to truly understand how it's made, we must step inside the walls of one of their advanced, high-security confectionery plants. It all begins with the hazelnut, Ferrero's signature ingredient. The company is one of the largest consumers of hazelnuts globally and maintains close relationships with farmers across Turkey, Italy, and Chile. Only whole, uniform, high-grade hazelnuts are accepted for use in Ferrero Rocher. Upon arrival at the processing facility, the hazelnuts are cleaned to remove debris, shelled, and subjected to multiple rounds of size grading and visual inspection, both by machine and by human eyes. The hazelnuts are then gently roasted in continuous drum roasters. These large, rotating cylinders apply indirect heat to evenly roast the nuts without scorching them. Temperature and time are tightly controlled, typically around 150-160 degrees Celsius for 15 to 20 minutes. The goal is to enhance the nut's natural oils and flavor without damaging the internal structure. Once roasted, the nuts are cooled rapidly to halt the cooking process, then transferred to storage under nitrogen to preserve freshness. With the hazelnuts ready, attention turns to the wafer shell, the crisp, spherical layer that surrounds each nut. The wafer is made from a batter of wheat flour, water, sugar, oil, and leavening agents. The batter is deposited onto heated hemispherical molds in automated wafer baking machines. These molds close like clamshells, sealing and cooking the wafer until it forms a hollow, thin sphere. This process takes only seconds, and each wafer shell is then cooled, trimmed, and conveyed to the filling station. Now we move to the cream filling. This smooth, chocolate hazelnut cream is made using a proprietary blend of ingredients: cocoa, milk powder, sugar, and hazelnut paste. The hazelnut paste is prepared by finely grinding roasted hazelnuts into a silky nut butter, then blending it with cocoa solids, vegetable oils, and emulsifiers. The mixture is heated, homogenized, and passed through conching units to develop a smooth texture and balanced flavor. At this point, multiple streams converge. A whole roasted hazelnut is placed in the center of each wafer hemisphere. Then, a precise amount of the chocolate hazelnut cream is deposited into the cavity, encasing the nut. The wafer sphere is closed by joining two halves together with a light pressure and a ring of filling acting as an adhesive. Each filled wafer is now a complete, delicate core, ready for the outer coating. The first coating is a layer of milk chocolate. The filled wafers travel along a conveyor through a curtain of tempered chocolate, a process called enrobing. The chocolate is kept at exact temperatures to ensure optimal viscosity and crystallization. Too hot, and it will be too thin and won't set properly. Too cold, and it will be too thick or bloom later on the shelf. The enrobing tunnel applies a uniform coat of chocolate that covers the wafer sphere entirely. Immediately following enrobing, the still wet chocolate is dusted with finely chopped, roasted hazelnut fragments. This is done through a synchronized nut dispenser that sprinkles fragments over the rotating, chocolate-covered spheres. The particles adhere instantly to the tacky surface, forming the crunchy outer texture that defines the Ferrero Rocher bite. From there, the products enter a refrigerated cooling tunnel to crystallize and harden the chocolate coating. This tunnel is kept at a consistent low temperature, typically around 10 to 12 degrees, with humidity controls to ensure shine and stability. Once fully cooled and set, the Ferrero Rochers pass through a final inspection system. High-speed vision cameras scan each sphere for cracks, missing nut fragments, or uneven coatings. Those that fail to meet visual standards are removed automatically by pneumatic diverters. The acceptable pieces then move into one of the most iconic parts of the process: foil wrapping. Ferrero's wrapping process is instantly recognizable. Each sphere is wrapped in a piece of gold foil, folded tightly by high-speed rotary wrapping machines that spin the foil around the product in a process similar to a ballet. The wrapping must be secure but not crumpled, an art that's perfected through decades of machine design and precision calibration. A paper band with the Ferrero Rocher logo is heat-glued around the equator of the foil, acting both as branding and as a seal of authenticity. Wrapped Rochers are then gently placed into brown fluted paper cups, which not only help with presentation, but also protect the spheres from scuffing. Robotic pick-and-place arms transfer the wrapped products into their cups and arrange them into trays or gift boxes. These boxes may contain 3, 12, 24, or even 48 pieces, depending on market and seasonal packaging. Secondary packaging lines group the gift boxes into cartons for shipping. These cartons are automatically assembled, packed, and sealed using robotic case packers. Once completed, the cartons are barcoded, weighed, and stacked onto pallets by robotic palletizers, then stretch wrapped and scanned into inventory. From here, they enter climate-controlled storage warehouses, awaiting shipment to distribution centers around the world. Of course, quality control is continuous throughout the entire process. Every batch of cream filling is lab tested for fat content, viscosity, microbial load, and texture. Wafer shells are tested for brittleness and moisture content. Chocolate is sampled for bloom potential, fat migration, and melting point accuracy. Finished products are subjected to sensory panels who evaluate every aspect of the bite, from crunch to melt to aftertaste. Behind all of this is a digital infrastructure that ties everything together. From syrup cookers to nut roasters to packaging robots, the plant is run by integrated SCADA and MES systems. These systems monitor temperature trends, downtime events, ingredient usage, and traceability data in real time. Each product can be traced back to its lot of hazelnuts, batch of chocolate, and shift team, allowing full accountability and rapid response in case of any deviation. What's more, Ferrero production plants place a strong emphasis on food safety. They are certified to international standards such as ISO 22000 and FSSC 22000, and operate with strict allergen segregation, hygiene zoning, and air filtration systems. Operators wear full protective gear, and certain areas are restricted to minimal human presence to reduce risk of contamination. Sustainability has also become a central pillar of Ferrero's operations. The company has invested heavily in traceable and responsibly sourced hazelnuts and cocoa. Many factories are now equipped with heat recovery systems, water recycling units, and energy-efficient machinery to reduce the environmental impact of confectionery manufacturing. Incredibly, this entire process, from nut to wrapped product, can happen in under 2 hours. That's 2 hours to roast, fill, coat, wrap, and package what looks like a handmade luxury. But it's not magic. It's manufacturing at its most precise. Every movement of every machine, every gram of chocolate, every foil fold is measured, managed, and monitored. The result is consistency across countries and climates. A Ferrero Rocher purchased in Rome will taste the same as one bought in Dubai, Tokyo, or Toronto. That uniformity is achieved not through simplicity, but through complex synchronization across ingredients, machines, and human craftsmanship. From a distance, Ferrero Rocher production might seem effortless, but it's anything but. It's a feat of edible architecture, where layers are stacked with millimeter accuracy, flavors balanced with chemical precision, and every aspect of the product calibrated to evoke delight, bite after bite. In a world of mass production, Ferrero has mastered the art of small indulgences at scale. Each gold-wrapped sphere is a symbol of how far food science and industrial artistry can go, not just to make chocolate, but to make joy. For over a century, Hershey's has been America's chocolate. With its iconic square segments, sweet creamy flavor, and unmistakable aroma, the Hershey's milk chocolate bar has become a symbol of comfort and nostalgia. But few realize how many complex steps, both agricultural and industrial, go into creating each one of those neatly molded rectangles. From cocoa plantations to high-tech factories in Pennsylvania and beyond, the making of a Hershey's bar is a feat of logistics, chemistry, and precision food engineering. It all begins thousands of miles away from the factory floor, in the equatorial regions where cocoa trees thrive. Theobroma cacao, the tree that produces cocoa pods, is cultivated in countries like Ghana, Côte d'Ivoire, and Ecuador. Each pod contains 20 to 40 cocoa beans encased in a sweet pulp. After harvesting, farmers ferment the beans under banana leaves or in wooden boxes for several days. This natural process transforms the bitter, raw seed into a flavor precursor for chocolate, deepening its complexity. The fermented beans are then sun-dried, bagged, and shipped by container vessels to Hershey's processing facilities. Upon arrival, the beans are cleaned to remove debris and sorted by origin, size, and quality. Each origin brings its own flavor profile. Ghanaian beans offer classic cocoa depth, while Ecuadorian beans may bring floral or fruity notes. The blending of these origins is what allows Hershey's to maintain a consistent, recognizable flavor year after year. Once cleaned, the beans enter the roasting drums, massive rotating steel cylinders where they are slowly roasted at controlled temperatures. This step develops the final flavor of the chocolate, similar to roasting coffee beans. Temperature and time vary depending on bean type, but typically range between 120-160 degrees Celsius for up to 45 minutes. As the beans roast, their shells become brittle, and the internal nibs, the part used to make chocolate, develop their signature aroma. The roasted beans are passed through a winnowing machine, which cracks them open and uses airflow to separate the light, papery shells from the heavier nibs. The nibs are now ready to become chocolate. They are ground into a thick, dark brown paste known as chocolate liquor, a 100% cocoa mass that contains both cocoa solids and cocoa butter. Despite the name, there is no alcohol in this liquor, just pure ground cocoa nib. From here, the real engineering begins. The chocolate liquor is combined with milk powder, sugar, and additional cocoa butter in large mixing tanks. The exact formula is proprietary, but we know Hershey's is famous for its milk-forward flavor and slightly tangy finish. That tang is believed to come from a special milk treatment process developed by Milton Hershey himself, involving controlled lipolysis. Essentially, the development of specific flavor compounds by partially breaking down milk fats under heat. Once the ingredients are mixed into a coarse paste, the mass is sent to 5-roll refiners, large steel roller mills that gradually grind the chocolate mixture down to a particle size of roughly 20 microns. This microscopic consistency is what gives chocolate its velvety texture. If the particles are too large, the chocolate feels gritty. Too small, and it may clump or fail to release flavor properly. Each roll in the refiner is set with increasing tightness to achieve a uniform grind. After refining, the chocolate is still dry and powdery. To transform it into a smooth liquid, it enters the conch, a key piece of equipment in chocolate making. The conch is a heated, agitating chamber where the chocolate mass is kneaded for hours. This process drives off residual moisture and undesirable volatiles, improves mouthfeel, and develops the final flavor. During this stage, emulsifiers such as soy lecithin are added to improve flow properties. Once conched to specification, the chocolate is ready for tempering. This critical step aligns the fat crystals in the cocoa butter to ensure a stable, glossy, and snappy final product. Tempering involves a carefully timed series of heating and cooling cycles, typically heating the chocolate to around 45 degrees Celsius, cooling it to 27 degrees Celsius, then slightly reheating to working temperature at about 31 degrees Celsius. This allows the formation of type 5 fat crystals, which give chocolate its desirable characteristics. Now tempered, the liquid chocolate is ready for depositing. It flows into stainless steel depositors, which dispense precise volumes of chocolate into bar molds. Each mold is preheated slightly to prevent premature crystallization and is vibrated to remove air bubbles and level the chocolate surface. Once filled, the molds enter a cooling tunnel, a refrigerated chamber where the chocolate solidifies into its familiar form. After cooling, the molded bars are ejected from the molds by gentle air pressure or mechanical release. Each bar is then conveyed to a high-speed wrapping line. For the classic Hershey's milk chocolate bar, this involves 2 layers, an inner foil or paper liner and an outer printed sleeve. Wrapping machines fold and seal the bars at speeds of hundreds per minute, using heat sealing and cold gluing methods. Each bar is also inkjet printed with a production code for traceability and inventory control. Wrapped bars are then counted, stacked, and loaded into cartoning machines for retail multi-packs or into larger cases for warehouse distribution. Robotic arms and conveyors carry the cartons to palletizers, which arrange them onto pallets in precise patterns. Pallets are stretch-wrapped, labeled, and scanned into warehouse inventory systems. Throughout the entire process, quality control is constant and rigorous. Samples from every batch are tested for fat content, sugar ratio, particle size, flavor, aroma, and shelf stability. Sensory panels perform taste tests to ensure the product matches Hershey's official flavor profile. Microbial testing ensures food safety, and all data is logged in digital batch records to ensure traceability and compliance with food safety standards like SQF, ISO 22000, and FDA regulations. Inside the factory, automation is central. From ingredient dosing and temperature control to tank agitation and mold handling, programmable logic controllers and SCADA systems monitor every parameter. Touchscreen panels give operators live insight into flow rates, cooling curve progress, and downtime tracking. These data streams not only keep the line running smoothly, but also help predict maintenance needs and optimize energy efficiency. Another remarkable component of Hershey's production is its environmental stewardship. Modern facilities recycle water used in cooling circuits, reclaim heat from conching motors, and repurpose off-spec chocolate by reworking it into other products. The cocoa shells removed during winnowing are even used as fertilizer or animal feed, reducing waste. Supply chain transparency is also part of the modern Hershey's commitment. Cocoa beans are increasingly sourced through certified sustainable programs, with investments in farmer education and ethical labor practices. Blockchain-based platforms now allow for bean-to-bar tracking, helping ensure that every bar supports both quality and responsible sourcing. Logistically, the bars are shipped to national and international distribution centers using temperature-controlled routes when needed. Warehouses use first-in, first-out inventory systems, and retailers receive shipments in compliance with demand planning forecasts. Each bar, despite traveling thousands of miles and passing through dozens of steps, remains precisely as Hershey intended: consistent, safe, and perfectly sweet. It's easy to take a chocolate bar for granted, to see it only as a snack or a treat. But what lies behind that silver and brown wrapper is a world-class production system that balances food science, mechanical engineering, flavor chemistry, and sustainable agriculture. From cocoa farms to Pennsylvania steel, from sugar silos to foil stampers, the making of a Hershey's bar is not just about chocolate. It's about heritage, process control, innovation, and the relentless pursuit of consistency in a product that's been enjoyed by generations. In every square, you taste more than just sugar and cocoa. You taste a supply chain running like clockwork, a formula calibrated to microns, and a commitment to quality that's lasted over 100 years. A Hershey's bar isn't just made, it's built, layer by layer, process by process, from the ground up. The production of Domino's pizza begins not in the store kitchens, but in massive regional supply chain centers, where the ingredients, particularly the dough, are produced in industrial quantities with an emphasis on consistency, quality, and efficiency. Before any pizza reaches the oven in a Domino's franchise, it starts its journey in these highly controlled factory environments where each element is formulated to exact specifications. The first and most critical component is the dough, which is made fresh daily in these centers and delivered under cold storage conditions to every Domino's outlet. The dough-making process begins with the arrival of bulk ingredients, including high-protein wheat flour, water, vegetable oil, yeast, sugar, and salt. These ingredients are stored in separate storage systems based on their physical state and volume requirements. Flour is kept in massive silos connected to the production floor through pneumatic tubing systems. These tubes transfer flour directly into the industrial-scale mixers with precise weight measurements, controlled by automated batching systems. Water, which must be maintained at a specific temperature range to activate the yeast properly, is stored in stainless steel tanks connected to digital flow meters. This ensures the exact volume is dispensed into each batch, typically to within 1/10 of a liter. Vegetable oil, sugar, salt, and yeast are also dispensed through closed-loop systems that prevent contamination while ensuring high-speed delivery and accuracy. The industrial mixers used at this stage are horizontal high-capacity spiral mixers or fork mixers, depending on the location and the specific equipment model in use. Each mixer is designed to handle hundreds of pounds of dough per batch, usually around 400 to 600 pounds. The process begins with dry ingredients being added first, followed by a controlled stream of water and oil. Once the mixture reaches the desired hydration point, the mixer operates at different programmed speeds to knead the dough until it reaches the correct elasticity and gluten development. This usually takes around 8 to 10 minutes, with temperature sensors embedded in the bowl to prevent overheating from friction, which can damage the yeast. As the dough mixes, factory floor operators monitor each batch's time, temperature, and consistency through a computerized interface. Every mixer is part of a larger manufacturing execution system that records batch data, ingredient lots, timestamps, and operator IDs. This traceability system ensures that if a problem ever arises, such as inconsistent rise or poor texture in a batch, managers can track it back to the specific flour lot or mixing time and make necessary adjustments for future runs. Once the dough reaches optimal consistency, it is automatically discharged from the mixer into a dough trough, which is essentially a wheeled stainless steel container that holds the dough until it's moved to the dividing station. The dough is then transferred into a hopper above a hydraulic or rotary dough divider. This machine uses either vacuum-assisted suction or mechanical cutting blades to portion the dough into uniformly weighted balls, typically ranging from 6 to 20 ounces, depending on the final pizza size. Each portion is measured by load cells, digital weighing systems that maintain accuracy within a few grams. These dough balls then proceed to the rounding machine, which takes each divided piece and rolls it into a tight, smooth sphere. This is crucial for creating the internal tension needed for a uniform rise during fermentation. The rounding machine uses rotating plates or belts that apply gentle pressure and a circular motion to the dough. After rounding, the dough balls are dusted lightly with food-grade flour or semolina to prevent sticking, and then placed into oiled dough trays. These trays are stacked and covered with plastic lids or wraps to maintain humidity and prevent surface drying. They're labeled with a printed barcode that includes the production date, time, dough type, and batch number. At this point, the dough enters the proofing phase, which is critical to developing both the structure and flavor of the final pizza base. Proofing occurs in temperature and humidity-controlled rooms, where racks of dough trays are stored for several hours. The ideal proofing conditions are generally around 80 degrees Fahrenheit with 75% relative humidity, although this can vary slightly based on factory location and yeast activity. The yeast begins to consume the sugars in the dough, producing carbon dioxide and ethanol as byproducts. This gas becomes trapped within the dough's gluten network, causing it to expand and develop the characteristic airy, chewy structure. Simultaneously, organic acids and alcohols created during fermentation start to build complex flavor notes in the dough. During the proofing period, plant operators conduct regular checks to monitor dough expansion, surface tension, and even internal temperature using infrared thermometers and visual inspection. Some factories use automated camera systems that scan the trays and calculate proofing progress by measuring the dough's rise and dome shape. Any deviations from the standard profile are flagged for intervention, whether that means extending the proofing time or moving certain trays to a different section of the proofing room. Once the dough reaches the desired level of fermentation, it is moved to the cold storage phase. In this stage, the dough trays are rolled into large walk-in refrigeration rooms, where the temperature is maintained at approximately 2 to 4 degrees Celsius. This halts the yeast's activity and locks in the developed flavor while also preventing overproofing. The chilled dough can now be stored for up to several days, depending on demand at the destination stores. During this time, the trays are rotated to maintain even cooling and are occasionally inspected for signs of over-fermentation or drying. While the dough is being prepared, Domino's is also handling the sauce production in parallel. Tomato sauce is made in separate processing areas, using high-volume stainless steel kettles equipped with agitators and heating jackets. The base of the sauce is tomato paste, which is diluted with water to reach a specific consistency. To this, measured quantities of salt, sugar, oregano, garlic, basil, black pepper, and other proprietary spices are added. Some locations use pre-mixed spice sachets that are batch-coded for accuracy, while others blend the seasoning on-site. The sauce mixture is heated to temperatures between 80 and 90 degrees Celsius to sterilize it and meld the flavors. Once the heating process is complete, it is rapidly cooled using a plate heat exchanger to bring it down to refrigerated storage temperature, usually 30 degrees Celsius, around 4 degrees Celsius. The cooled sauce is then transferred into food-safe storage containers often in 10-liter or 20-liter units, and sealed with tamper-evident caps. Each container is labeled with a batch code and production date before being staged for shipment alongside the dough. In addition to sauce, the factory prepares other key ingredients, including shredded cheese and select toppings. The cheese used in Domino's pizzas is typically a low-moisture mozzarella, known for its excellent melting properties and stretch. Some supply centers receive the cheese in bulk blocks and shred it in-house using high-speed rotary shredders that slice the blocks into uniform strands. The shredding process includes a light coating of anti-caking agents like potato starch or cellulose to prevent clumping during storage. The shredded cheese is packed into portioned bags, vacuum sealed, and stored under refrigeration. Once all ingredients, dough, sauce, cheese, and prepped toppings are ready, they are organized and loaded into refrigerated delivery trucks. These trucks operate under a tight logistics schedule, making daily or multi-day trips depending on the volume needs of each Domino's franchise store. The internal temperature of each truck is continuously monitored using GPS-integrated data loggers, and real-time data is fed back to the supply center's central operations system. This ensures that if any deviation in temperature or route timing occurs, corrective action can be taken immediately. By the time the products arrive at the store, they are fully prepared and only require assembly and baking. The franchise stores then execute the final steps of pizza preparation, which involves pressing out the dough, saucing, topping, baking, and packaging. However, the factory's role is absolutely central to ensuring that every ingredient arrives at the exact same standard, no matter where the pizza is being made or consumed. Through this centralized and automated model, Domino's achieves consistency at a global scale, while minimizing waste and human error in the earliest and most foundational stages of production. Once the refrigerated trucks deliver the dough, sauce, cheese, and toppings to each Domino's franchise, the handling of those ingredients transitions from centralized factory production to carefully structured in-store processes that continue to follow standardized protocols. However, the factory's influence is far from over at this point. The store-level procedures are engineered to mirror the consistency, precision, and speed found in the supply chain centers, effectively extending the factory environment into each retail location. Inside the store, the first critical action is the proper storage of the dough. As the dough trays arrive straight from cold storage, they are transferred into the store's walk-in refrigerator, where they are kept at a consistent temperature of 2 to 4 degrees Celsius. Each dough tray remains sealed with its identifying barcode, which includes the production batch, date, and shelf life. This code is scanned upon arrival, logged into the store's inventory system, and linked to the store's daily forecast so the staff can prioritize older dough for earlier use, following a strict first in, first out system to ensure freshness and prevent waste. Before the dough can be used for making pizzas, it needs to temper. Cold dough straight from refrigeration is too stiff and contracted to stretch evenly or bake correctly. Therefore, several trays are pulled from the cooler in staggered intervals and placed in a proofing area within the store, typically kept at room temperature for 30 to 60 minutes. During this period, the dough relaxes, allowing the gluten to become more extensible and the yeast to reawaken slightly, which enhances browning and flavor development in the oven. This step also restores some of the softness and elasticity necessary for the dough to perform consistently on the preparation line. The next key phase in the process is dough pressing or hand stretching, which transforms the proofed dough ball into a pizza base. Depending on the store's equipment and regional preferences, Domino's uses one of several standard methods for this. In many high-volume locations, a mechanical dough press is employed. This press is a heated platen system where a single dough ball is centered between two metal plates. With controlled pressure and temperature, the plates compress the dough to the specified diameter and thickness. The brief heat exposure also helps to set the edge of the crust slightly, which prevents overexpansion during baking. Other stores use hand-stretching techniques, which involve manually flattening the dough using the palms and fingertips to create an even disc, often followed by a gentle spinning motion to widen it to the correct diameter. Employees are trained to feel for even dough resistance, check the uniformity of thickness, and ensure the edges are slightly thicker to create the signature Domino's crust ring. Some locations employ a dough sheeter, a machine that flattens dough between two adjustable rollers, which is commonly used for medium thickness crusts or thin crust options. Once the dough is properly shaped and placed on a pizza screen or baking tray, it is ready to be sauced. The sauce comes in pre-measured containers or large bag-in-box systems with pump dispensers, depending on the store's volume. A standardized rotary sauce ladle or domed saucer is used to apply a precise amount of sauce, usually between 90 and 120 grams for a medium pizza. The sauce is spread using a circular motion that stops approximately 1 inch from the crust edge to allow for natural bubbling and rim development during baking. With the base sauced, the next step is the cheese application. Domino's cheese is a proprietary, low-moisture mozzarella blend, optimized for melt, stretch, and browning. The cheese arrives shredded in sealed, chilled bags and is stored in under-counter refrigeration near the prep stations for quick access. Employees use color-coded scoops to portion out exact grams of cheese per pizza size: small, medium, large, or extra large. This consistency ensures that the cheese melts evenly and that the nutritional and caloric values remain standardized. In high-throughput stores, preloaded portion dispensers or weigh scales may also be integrated into the cheese station to reduce time and improve accuracy. Next, the pizza moves to the topping stage. Domino's toppings, such as pepperoni, Italian sausage, mushrooms, green peppers, onions, olives, jalapenos, grilled chicken, and bacon, are kept in ingredient rails with stainless steel pans, maintained at safe refrigeration temperatures using undermounted chillers. Each topping has a designated scoop or set of tongs, and employees are trained to apply the correct amount and distribution per pizza size and recipe. Toppings are applied in a set sequence to ensure even cooking and consistent flavor layering. For example, pepperoni slices are laid edge to edge to cover the surface in a signature circular pattern, while sausage crumbles are more scattered to allow airflow between pieces. Vegetables are typically added last, as their moisture content can impact the crispness of the crust if layered too deeply. Domino's uses laminated guides and portion charts to ensure that every pizza, regardless of who's preparing it, looks, weighs, and tastes the same. With the pizza fully assembled, it is placed onto a conveyor belt oven, also known as an impingement oven. This oven style uses jets of superheated air blasted from top and bottom to ensure even baking. The oven belt is set to a precise speed, generally resulting in a 5.5 to 7 minute bake time, depending on the pizza size and topping density. The oven's digital interface allows staff to select different profiles for thin crust, hand-tossed, deep dish, or extra cheese options. Each profile adjusts air velocity, top and bottom heat ratio, and belt speed to produce the ideal bake for that style of pizza. During baking, several chemical and physical transformations take place. The crust expands slightly from the final stage of yeast fermentation. Steam is released from the sauce and toppings, and the cheese melts and begins to brown through the Maillard reaction. Excess moisture from vegetables is evaporated by the oven's airflow, ensuring the crust remains crisp and doesn't sag. The pizza emerges from the other side of the oven, fully baked and ready for slicing. At the end of the conveyor, pizzas are transferred to a staging counter, where they rest for 20 to 30 seconds to allow the cheese to set slightly. Then, using a rocker blade or circular pizza cutter, employees cut the pizza into standard portions, usually 8 slices for a large pizza, based on Domino's cutting guides. Each pizza is then slid into a branded corrugated cardboard box, which is specially designed with vent holes and moisture-absorbing liners to preserve crispness during delivery. Every box is sealed and receives a printed label generated by the store's order management system. This label includes the customer's name, order number, timestamp, and pizza specifications. For orders placed online or through the app, this also triggers an update on Domino's proprietary pizza tracker, which uses real-time data from kitchen sensors to notify customers of each stage, from dough prep to oven entry, baking, boxing, and out for delivery status. Throughout the day, all these processes are monitored for compliance with Domino's global standards. District managers conduct regular audits using detailed checklists covering dough handling, oven cleanliness, bake quality, topping accuracy, and safety procedures. Additionally, Domino's has built-in kitchen timers and alert systems that ensure no dough is held at room temperature too long, no pizzas sit unboxed beyond the quality threshold, and no ingredients are used past their hold times. Each store's operations are built to match the precision and consistency of the supply chain factories. In fact, many stores undergo periodic retraining sessions to realign their practices with the upstream factory procedures. This ensures that no matter how far the finished product is from the centralized dough production, the final experience to the consumer remains nearly indistinguishable between one location and the next. As soon as a Domino's pizza is sliced and boxed, the journey continues into a carefully engineered phase focused on preserving product quality and maximizing delivery efficiency. At this point, what might appear to the customer as the simple act of putting a pizza in a box and sending it out the door is, in reality, a continuation of Domino's factory-grade systems, refined, tracked, and executed with industrial precision. Each Domino's box is made of specially designed corrugated cardboard, engineered not only to be structurally strong enough for stacking and transportation, but also to allow moisture control and thermal retention. Small vent holes are strategically placed around the box edges to allow steam to escape without sacrificing internal heat. This is critical to maintaining a crisp bottom crust while keeping the cheese and toppings hot and intact during transit. The liners inside some specialty pizza boxes also use grease-resistant coating and moisture-wicking micro layers that reduce sogginess, especially in pizzas with heavier vegetable or meat toppings. Once the pizza is placed in its box, a label is immediately printed and applied. This label contains all relevant details: the order number, pizza type, time of bake, the customer's name and address, and specific cooking instructions if applicable, like extra crispy crust, light sauce, or no cheese. More importantly, the label also includes digital timestamps and batch codes that tie the finished product directly back to every earlier phase of production. These codes link the order to its dough batch, sauce mix, cheese lot, and even the name of the employee who boxed it. This allows full traceability, and in the event of a customer complaint or quality issue, managers can pull up detailed records to investigate and resolve the problem efficiently. The next link in the process is the delivery system, which Domino's has industrialized to a level similar to its supply chain and production operations. Every Domino's location uses a centralized digital system to optimize delivery routes, monitor driver location, and track pizza temperature using estimated time-to-door algorithms. In some urban areas or flagship locations, Domino's even uses thermal sensors and GPS modules in the delivery bags themselves. These sensors ensure that the pizza never drops below the acceptable temperature threshold. typically around 140 degrees Fahrenheit or 60 degrees Celsius, which maintains cheese integrity and topping stability. The delivery bags used are not basic insulated containers. They are purpose-built thermal sleeves with advanced insulation material, sometimes incorporating phase change materials that hold heat without overheating the product. These bags are lined with aluminum and closed with Velcro or zippers to ensure no heat escape. In some pilot programs, Domino's has experimented with electrically heated delivery pouches that plug into the vehicle's charging outlet, maintaining a regulated temperature across the entire delivery window, especially in colder climates. While the pizza is en route, Domino's proprietary pizza tracker remains active. This cloud-based interface receives inputs from multiple sources: the POS system, kitchen sensors, label printer, and delivery dispatch terminal, and creates real-time updates for the customer. As soon as the order is marked out for delivery, a countdown begins based on predictive delivery timing, factoring in distance, time of day, historical traffic data, and driver availability. This transparency not only improves customer satisfaction, but also provides performance data for internal use. Behind the scenes, Domino's aggregates all this operational data into their enterprise-wide performance dashboards. Each store's key performance indicators, such as order accuracy, delivery time, baking efficiency, and customer satisfaction scores, are updated daily. Store managers and regional supervisors review these metrics in regular meetings, identifying trends, deviations, and opportunities for improvement. If a certain franchise location consistently shows slower bake times or increased complaints about cold pizza, it may trigger a maintenance review of the oven system or retraining of kitchen staff. Meanwhile, at the supply chain level, Domino's uses reverse logistics to complete the factory-style loop. Once a delivery is completed, used ingredient bins, dough trays, and empty sauce containers are returned to the regional supply centers on the next inbound truck trip. These items are cleaned, sanitized, and reused according to food safety protocols. Reusable dough trays, for example, go through automated washing systems that use high-pressure jets, detergent, and thermal sanitation to prepare them for the next production cycle. By managing both outgoing and incoming flows efficiently, Domino's minimizes waste and maximizes logistical efficiency, keeping the system sustainable and cost-effective. Beyond the visible kitchen and delivery operations, there is also a sophisticated forecasting and inventory management system that relies heavily on factory data. Using AI and machine learning, Domino's forecasts demand for dough, sauce, cheese, and toppings at each store based on variables like local events, weather, historical order volumes, and even social media trends. This information is transmitted back to the supply chain centers, which adjust dough production and ingredient packaging accordingly. For example, if a city is expecting a snowstorm, the system may predict a spike in delivery orders and increase dough production by 10% for the affected stores. This tight integration between forecasting and factory production minimizes spoilage and overproduction, ensuring that only as much dough and sauce is produced as will be used within a defined freshness window. The same logic applies to toppings and cheese. Ingredients that are nearing the end of their shelf life can be flagged automatically, prompting store managers to run promotional offers or bundle deals to encourage faster turnover. By linking the retail environment back to the factory floor, Domino's achieves a level of responsiveness and precision rarely seen in traditional food service operations. Domino's also incorporates periodic updates and R&D feedback into its manufacturing systems. When a new product is launched, such as a specialty crust or a new line of toppings, the manufacturing centers adapt their formulations and packaging processes to accommodate the change. For instance, a new crust option may require a dough with a different hydration level or proofing profile. In that case, dough mixes are recalibrated, proofing room settings adjusted, and additional QA steps introduced. The product launch timeline includes upstream changes that affect every supply chain center, down to the labeling system and transport logistics. To maintain global brand consistency, Domino's has standardized its production protocols across all countries, yet also incorporates regional customization. For instance, the dough produced in India may include slight formulation changes to better suit local humidity levels or flour types. In Japan, where crust styles vary, dough mixing and resting procedures may be adapted for fluffier or rice-infused bases. However, the core manufacturing principles, precise batching, automated mixing, cold chain delivery, and digital inventory tracking remain consistent regardless of geography. Domino's also performs routine auditing and calibration of their supply chain centers to ensure continued alignment with performance standards. Factory equipment such as mixers, dividers, and temperature control units are subjected to preventive maintenance and calibration checks at regular intervals. Technicians verify dough density, elasticity, and yeast activity using physical measurements and digital readouts. Similar checks are done for sauce viscosity, cheese fat content, and topping moisture levels. These numbers are logged and analyzed to identify any drift from target specifications, allowing corrective measures to be implemented before product quality is affected. Even packaging materials go through quality control. Corrugated boxes are tested for burst strength, fold endurance, and thermal retention properties. Adhesives used for box sealing are food safe and resistant to temperature extremes. The printing quality on labels is monitored to ensure clarity and durability, as these labels serve both customer-facing and internal traceability functions. Everything down to the ink used on packaging is selected for durability under heat and moisture, a testament to the factory-level thinking that permeates the entire Domino's ecosystem. The manufacturing journey of Doritos begins long before the chips ever hit the fryer or the seasoning drums. It starts in the cornfields. Doritos use a specific variety of whole kernel yellow corn selected for its starch content, moisture levels, and particle uniformity after grinding. The corn is harvested at peak maturity and tested for aflatoxins, foreign material, and protein content before it's even accepted at the plant. Only corn that passes this first round of quality standards is brought in for processing. At the factory, truckloads of bulk corn arrive daily and are funneled into underground receiving pits that use gravity to guide the kernels onto conveyor belts. These conveyors feed the kernels into the first stage of preparation, the cleaning and sorting system. In this system, the corn passes through an array of vibrating sieves, rotating drum sifters, and powerful pneumatic air classifiers. Large debris like cobs, sticks, or stones are removed first. Then, finer contaminants like dust and small broken kernels are extracted using aspirators that draw away lightweight particles. Magnetized rollers also scan the corn flow to remove any traces of ferrous metal, ensuring total cleanliness before cooking. Once cleaned, the corn moves into the nixtamalization phase, a crucial and traditional process that transforms the flavor, texture, and nutritional properties of the corn. Nixtamalization involves cooking the whole kernels in a large stainless steel vat of hot water mixed with food-grade calcium hydroxide, also known as slaked lime. The corn is cooked at around 85 to 90 degrees Celsius for approximately 20 to 40 minutes, depending on the batch size and corn variety. This lime water solution serves several purposes. It breaks down the outer pericarp of the kernel, making it easier to grind and digest. It also increases the bioavailability of niacin, softens the internal structure of the corn, and imparts the distinctive flavor profile that Doritos are known for. After cooking, the corn is not immediately processed but left to soak, usually for 8 to 12 hours in the same solution. This extended soaking allows the lime to fully penetrate the kernel and continues the softening and flavor-enhancing process. After the soaking phase, the corn is drained and rinsed thoroughly in large industrial washers that spray it with jets of clean water while gently tumbling the kernels. The goal is to remove the loosened pericarp, excess lime, and any residual cooking liquid. What remains is called nixtamal, a soft, pliable corn mass that still holds the shape of whole kernels, but has a meaty, hydrated texture. The nixtamal is now ready to be ground into masa, the dough-like base of every Dorito chip. The grinding is performed using industrial stone mills, rotating horizontal stones made of volcanic rock or synthetic composites, precisely aligned to maintain a consistent grind size. The nixtamal is fed between the stones, and the pressure shears the softened corn into a dense, cohesive paste. This paste is the masa, and its texture is critical. It needs to be soft enough to press, but dry enough to hold shape without sticking. Operators continuously monitor the temperature of the mesa during grinding. Too much friction can overheat the dough, which affects the final chip texture. Ideal mesa temperature coming off the stones is around 45 to 55 degrees Celsius. Viscosity is checked using inline sensors that measure flow resistance, and if adjustments are needed, small amounts of water or returned dry mesa are mixed back in using an automated feedback loop. Now, it's time to form the masa into flat sheets. The ground mesa is transported via auger screws into a sheeting machine, which extrudes the dough between two polished stainless steel rollers. These rollers are adjustable to control sheet thickness down to the millimeter, usually targeting between 1.2 and 1.8 mm, depending on the final chip specification. The mesa sheets are laid directly onto a continuously moving conveyor belt that carries them to the cutting station. The cutting system is a rotary die cutter, a high-speed drum outfitted with rows of equidistant triangular blades, each perfectly matched to the iconic Doritos shape. As the mesa sheet moves beneath the drum, the rotating blades stamp out thousands of identical triangle chips per minute. Each cut is sharp and precise, with just enough spacing to leave minimal waste dough between cuts. The trimmings, the thin slivers of masa between triangles, are not discarded. They are automatically lifted via vacuum collection and returned to the start of the sheeting process. These scraps are reincorporated into the fresh dough, ensuring efficient use of material and maintaining consistency. The cut triangle chips now move on a flat conveyor to a brief baking phase, which we'll explore in detail in the next section. This preliminary baking is vital to reduce moisture and stabilize the chip before it enters the high heat frying zone. But before any oil is introduced or seasonings are applied, this early stage, cleaning, nixtamalization, grinding, sheeting, and cutting, is where the foundation of Doritos' crunch, shape, and flavor truly begins. Once the precisely cut mesa triangles are formed and conveyed forward, they reach one of the most critical transitions in the Doritos factory, the pre-baking zone. Though often overlooked, this short but essential phase serves as a structural stabilizer that prepares each chip for frying without deforming, bubbling uncontrollably, or becoming overly saturated with oil. This stage controls the internal moisture content and builds the texture foundation that will result in the signature crunch. The masa triangles, still soft and slightly tacky from the sheeting process, move onto a continuous metal mesh conveyor belt that leads directly into an industrial tunnel oven. This pre-bake oven is not designed to fully cook or brown the chip. Instead, its primary goal is to reduce the moisture level from roughly 50% down to about 25 to 30%. This ensures the surface of the chip becomes firm enough to hold its shape when exposed to hot oil, but not so dry that it resists expansion. The oven itself is typically divided into multiple thermal zones. The first zone begins around 160 degrees Celsius, gradually increasing to about 260 degrees Celsius by the final section. Heated air is circulated by high-velocity blowers, creating a turbulent flow across the top and bottom of the chips to ensure uniform dehydration. The baking conveyor is made of stainless steel mesh that allows hot air to penetrate from below, guaranteeing that no side of the chip is undercooked. Sensors monitor humidity at various checkpoints, and real-time data is fed into the oven's PLC system to dynamically adjust airspeed and temperature depending on fluctuations in mesa density, ambient humidity, or line speed. As the chips exit the oven, they emerge firmer, drier, and more resilient, yet still pale in color and lacking the blistered surface texture that defines a finished Dorito. That transformation happens in the next stage, the continuous fryer system. Here, the par-baked chips fall gently off the oven belt and descend onto the infeed section of a massive open surface fryer. The fryer itself is a high-capacity stainless steel vessel filled with continuously filtered cooking oil. Most Doritos production lines use either corn oil, sunflower oil, or a proprietary blend of vegetable oils chosen for their high smoke points and neutral flavor profiles. The oil is maintained at a stable frying temperature of approximately 180 degrees Celsius, with variations of only +2 GC allowed during operation. Chips are submerged in the oil for about 35 to 55 seconds, depending on their exact moisture level and thickness. The chips ride through the fryer on a submersion conveyor, essentially a mesh belt with downward pressure bars that keep the chips fully immersed while preventing stacking or overlap. This is crucial because the frying process is not just about dehydration, it's about vaporization. As the residual water inside each chip turns to steam, it forces itself outward, puffing the chip slightly and creating those micro blisters and bubbly textures on the surface. This internal steam pressure is carefully managed. Too little and the chip stays flat and hard. Too much and it balloons into a hollow pocket. Above the fryer, exhaust hoods pull away steam and vaporized oil particles, filtering them through a heat recovery system that can reuse waste heat to pre-warm incoming oil. This system conserves energy and helps maintain a cleaner frying environment. The oil itself is constantly recirculated through centrifugal filters and fine mesh screens to remove crumbs, starch residues, or burnt particles. Fresh oil is added in controlled volumes throughout the day to maintain chemical balance and replenish lost volume. Once fried to the optimal light golden color, the chips are lifted from the oil by an outfeed conveyor and immediately pass through a vertical de-oiling section. Here, powerful centrifugal blowers aimed at precise angles blast away excess surface oil. This keeps the chips crispy, prevents pooling in the packaging stage, and ensures that the seasoning will stick without creating grease buildup. The chips then pass through an ambient cooling tunnel to bring them quickly down to room temperature. Cooling is not merely for worker safety, it stabilizes the fat within the chip and prevents condensation when entering the seasoning drums. Now comes one of the most defining stages of the entire process: seasoning application. Each Dorito must carry the bold, vibrant flavor profile it's known for, whether that's nacho cheese, Cool Ranch, spicy sweet chili, or any of the dozens of global variants. The seasoning powder itself is a proprietary blend of flavorings, including real cheese powders, spices, salt, sugar, yeast extract, and encapsulated flavor oils that deliver controlled release bursts of taste. The chips are conveyed into a rotating seasoning drum, an inclined, slowly turning cylinder lined with food-grade stainless steel. As the chips tumble over one another, a dry powder dosing system mounted above the drum applies the seasoning using precision augers and dispersing nozzles. These nozzles can spray a uniform mist of oil if needed before the seasoning hits, which enhances adhesion for certain formulations. The rotation speed of the drum, the flow rate of the powder, and the incline of the system are all adjustable and carefully tuned. Too slow, and the powder won't distribute evenly. Too fast, and the chips may break, or the powder may collect unevenly on some sides. Optical sensors track the color and surface reflectivity of the chips as they exit the drum. If the reflectivity is too high, that could indicate under-seasoning. If it drops below a preset threshold, over-seasoning may be occurring. This live data is fed back into the controller, which tweaks the feed auger speed or pauses the oil spray accordingly. The seasoning drum is one of the most customized parts of the Doritos line. Different flavors use different particle sizes, densities, and oil volumes, which means the drum design and spray system must adapt depending on the product. Some drums include vibrating baffles or spiral lifts that increase tumbling action for extra thick chips or extra coarse seasoning. Once seasoned, the chips are directed into the weighing and bagging system, but before that, they undergo an automated inspection phase. High-speed vision cameras scan every chip for size, shape, and color. Broken chips, overly curled pieces, or visibly under-seasoned chips are removed via air-jet rejectors. These rejected chips are collected and sent either for regrinding or biomass energy use. Only chips that pass inspection enter the multi-head weighers, machines equipped with a dozen or more radial weighing hoppers. These hoppers constantly drop chips into a central collection bucket when the combined weight equals the target for each bag, typically between 28 g and 198 g, depending on package size. Once a precise combination is reached, the chips are dropped into a vertical form-fill-seal bagging machine. Here, continuous rolls of metallized polypropylene film are formed into tubes, sealed along the sides, and crimped at the bottom. The weighed chips are dropped into the formed bag tube just before the top is sealed and cut. Each bag is nitrogen flushed to displace oxygen, extending the product's shelf life and preserving crunch. Then, the bags are labeled, batch coded, and pass through a final metal detector before being boxed for palletization. After the freshly seasoned Doritos chips are individually weighed, bagged, sealed, and inspected, the production line moves into the critical post-packaging and logistics phase, where efficiency and traceability become as important as taste and texture. Though the chips are now fully formed and flavor complete, the operation is far from over. In fact, from a manufacturing systems perspective, the next stages, palletization, storage, shipping, and quality verification, are just as sophisticated and optimized as any in the earlier production line. The newly filled Doritos bags exit the form-fill-seal machines onto a series of conveyor belts designed to collect, orient, and organize them by SKU, bag size, and flavor variant. These conveyor lines merge into case packing stations, which use robotic arms equipped with vacuum suction grippers or gentle mechanical paddles to lift and place the chip bags into cardboard cartons. These boxes are pre-folded, glued, and printed with relevant product information, including product code, flavor, best before date, factory location, and a scannable QR or barcode that links to all production details. Each carton is inspected for weight and shape before it moves to the next phase. Even slight deviations in shape, caused by mispacked bags or an uneven number of chips, can disrupt downstream palletizing operations, so edge integrity and sealing quality are monitored automatically using high-resolution 3D scanning systems. Any carton that fails to meet dimensional tolerance is rejected from the main flow and rerouted for manual inspection or reboxing. Once cleared, the filled cartons are transferred to automated palletizing stations. In most modern Doritos factories, this process is entirely robotic. A multi-axis robotic arm lifts groups of cartons and stacks them onto wooden or composite pallets according to a predefined stacking pattern optimized for shipping efficiency and stability. These patterns are determined by a logistics algorithm that accounts for box dimensions, weight distribution, and the pallet's ultimate destination, whether that's a domestic warehouse or a long-haul overseas container. After each pallet is completed, a robotic stretch wrapper encircles it with several layers of clear plastic film to stabilize the load. A printed pallet ID label is affixed, containing detailed information about its contents, including product types, quantities, batch numbers, and destination. These labels are scanned into the warehouse management system, linking each pallet to the larger production database in real time. From here, pallets are routed into the warehouse zone. Doritos production facilities feature climate-controlled warehouses designed to maintain product quality throughout the storage period before distribution. These zones are not refrigerated, as Doritos are shelf-stable, but they are meticulously managed to avoid conditions that could lead to staleness or packaging deformation. Temperatures are generally held between 18-22 degrees Celsius, and humidity is controlled below 50% to prevent foil bags from absorbing moisture or warping. Inventory in the warehouse is managed by automated storage and retrieval systems. Tall racking structures are navigated by robotic cranes that pick and place pallets based on real-time demand, stock rotation policies, and shipping schedules. Each pallet's position in the warehouse is logged down to the specific shelf and column level, making retrieval highly efficient. The warehouse management system is integrated with the factory's enterprise resource planning software, ensuring that production and distribution are fully synchronized. While in storage, every pallet of Doritos is subject to randomized quality control sampling. A team of trained technicians removes sample bags from various pallets across shifts and production lines and sends them to a separate sensory evaluation lab within the facility. Here, samples undergo a series of tests: mechanical compression for bag integrity, gas analysis for nitrogen content, and oxygen intrusion, seasoning density checks, and most importantly, taste and crunch testing. Crunch is measured using a texture analyzer, a machine that applies controlled force to the chip and records resistance, fracture point, and acoustic feedback. The results are compared to golden standard reference chips to determine if the texture profile remains within acceptable limits. Seasoning adhesion and intensity are tested via flavor profile mapping, and every element from saltiness to umami to residual aftertaste is scored and compared against target values. If a trend of inconsistency is detected, an investigation is initiated, often leading to a review of upstream production parameters like fry temperature variability, seasoning drum throughput, or even ingredient batch variations. This closed-loop system helps prevent long-term quality drift and enables real-time course correction. Beyond the factory, the logistics infrastructure that gets Doritos from warehouse to retail shelves is another marvel of scale and precision. The factory works in tandem with PepsiCo's broader distribution network, which includes regional distribution centers, cross-dock terminals, and last-mile delivery nodes. Based on retail demand forecasts drawn from sales data, seasonal trends, and real-time POS metrics, shipment volumes are adjusted dynamically. This avoids overproduction and waste while ensuring retailers remain stocked. Each shipment of Doritos is accompanied by a digital bill of materials, which includes all traceability data from ingredient sourcing to packaging and palletization. This document allows not only for internal tracking, but also rapid action in the event of any product recall or customer complaint. If an issue is raised about a particular bag, say under-seasoning in a certain region, operators can trace the issue back to a specific lot, machine, shift, and even the original corn batch used in production. Globally, the manufacturing process for Doritos is also adapted based on regional consumer preferences and regulatory standards. While the foundational steps remain consistent: nixtamalization, sheeting, cutting, frying, and seasoning, the recipes and specifications can vary significantly. For example, in the US, cheese-based seasonings often use cheddar powder and lactic acid for tang, while in the UK or India, formulations may include less salt or alternative flavor enhancers to meet local guidelines or taste expectations. In markets like Japan or South Korea, where flavor sophistication and novelty are highly valued, factories produce limited edition Doritos featuring ingredients like wasabi, squid ink, or yuzu citrus. These variations often require changes in seasoning particle size, oil stability, or packaging material, and as such, the production lines must remain flexible. To facilitate this, Doritos factories use modular flavor dosing systems and quick changeover machines that allow seamless transitions between variants with minimal downtime. In addition to this flexibility, Doritos production lines are increasingly being outfitted with smart factory technologies. These include IoT sensors, predictive maintenance platforms, and AI-driven scheduling software. For instance, a vibration sensor might detect a subtle change in the seasoning drum's motor function that suggests a bearing is beginning to fail. Rather than waiting for a breakdown, the system automatically schedules maintenance during a planned production lull, avoiding unplanned downtime. Energy efficiency is also a growing focus. Waste heat from the fryers is often recovered through heat exchangers and used to preheat water for the nixtamalization tanks or warm the air in the seasoning room. Air filtration systems recycle hot air from the fryer exhaust into the building's HVAC to reduce natural gas usage. These sustainability practices help reduce both costs and environmental impact. Waste reduction is another area of innovation. Trimmings from mesa sheeting, broken chips, and seasoning dust are no longer treated as loss. Instead, they're collected, analyzed, and often reused in animal feed production, compost systems, or converted into biofuel at third-party processing facilities. Factory waste targets are set annually, and each production shift is scored on both yield efficiency and environmental impact. Ultimately, the journey of a Dorito from corn kernel to crunchy triangle is one of constant refinement. At every stage, whether it's dough hydration, fryer calibration, seasoning density, or robotic case packing, the process is governed by a matrix of mechanical precision and human sensory experience. The chips may seem simple to the average consumer, but behind every bag lies a production system that blends food science, industrial engineering, supply chain logistics, and consumer psychology into one unmistakable result: bold flavor, addictive crunch, and global brand consistency. It all starts with the Consumer Insight Team, which continuously analyzes sales data, social media trends, cultural food movements, and even fine dining innovation to identify gaps or opportunities in the market. A spike in interest around birria tacos, for example, might inspire a spicy beef consommé Doritos concept. Once a viable trend is spotted, food scientists and flavor chemists work alongside marketing strategists to develop flavor direction briefs, detailed documents that outline the intended taste profile, emotional positioning, and target audience. In PepsiCo's Flavor Innovation Centers, teams begin with flavor mapping. This involves breaking down target flavors into their basic aromatic and taste components. For a concept like Flamin' Hot Dill Pickle, the scientists would analyze heat components, acidity, herbal notes, and salt balance. Using GCMS, flavor chemists extract and replicate aromatic profiles to ensure they match real-life foods as closely as possible. Next, benchtop seasoning blends are created in small batches using food-grade flavor powders, encapsulated oils, anti-caking agents, and natural extracts. These are applied to test chips using miniature tumblers that mimic the behavior of full-scale seasoning drums. Each test batch is evaluated by sensory panels, trained tasters who assess flavor intensity, balance, aftertaste, aroma, and how the flavor interacts with the chip's natural corn and oil base. Their feedback is mapped against a flavor wheel to identify gaps or off notes that require reformulation. Multiple iterations are often needed. Some spices may clump, certain acids might degrade in heat, And some flavor oils could lose their punch after just a few days in packaging. Stabilizers and carriers are used to protect volatile components, and microencapsulation techniques ensure that heat-sensitive ingredients only release during mastication, not while sitting in the bag. Once the flavor passes internal panels, the next phase is consumer testing. In select cities, Doritos organizes blind taste tests, sometimes with up to 500 participants per flavor. Reactions are scored not only on flavor, but on memorability, uniqueness, and potential repeat purchase behavior. Statistical modeling software crunches this data to identify the most promising formulas. When a flavor is approved, it must be scaled up to factory levels without losing its integrity. Seasoning blends are manufactured in industrial blenders, often in batches of hundreds of kilograms. The bulk seasoning is tested for particle size, uniformity, moisture absorption, and flow behavior. During this phase, the seasoning is often reformulated slightly for stability, color consistency, and performance under high-speed drum tumbling. Then come the pilot runs. A limited quantity of chips is produced on a full-scale Doritos line using the new flavor. This lets engineers monitor how the seasoning behaves under actual production conditions, how well it sticks to the chip, whether it builds up on machinery, how the oil in the powder affects packaging line sensors. If issues arise, tweaks are made not just to the formula, but to the machinery settings as well. Finally, once all checks are passed, the new flavor enters full production, often accompanied by bold marketing campaigns and timed releases. Global coordination ensures that ingredients meet regional compliance, and new flavors often debut in test markets before rolling out broadly. These launches are tracked in real time, and consumer response loops back into the development pipeline, influencing which flavors stay, evolve, or disappear. This highly coordinated, scientific, and iterative approach allows Doritos to launch daring new flavors while maintaining the consistency and production efficiency that a global brand demands. Each new taste starts with creativity, but ends in finely tuned, factory-scale execution.